Marbles, soccer balls, and baseball bats only look simple because the hardest part is hidden inside them. A marble has to cool into a flawless sphere, a soccer ball has to survive impact without losing its flight, and a baseball bat has to be shaped from wood that won't crack with one hard swing. In this video, we uncover how 3 sports products are made in factories, and their processes are far more complicated than you think. Marbles emerge from the polishing drums with a deep glassy shine, rolling across vibrating conveyors like hundreds of tiny mirrors catching the factory lights from every direction. At first glance, they appear completely finished, but one final inspection still waits ahead, and it is surprisingly unforgiving. A single air bubble trapped too close to the surface, a swirl that drifted slightly off center, or a diameter that varies by less than a fraction of a millimeter can remove an otherwise perfect marble from the production line. That level of precision begins long before the polishing stage, because every marble starts as nothing more than carefully measured raw minerals that must first become perfectly molten glass. The process begins with massive storage silos holding the ingredients that will eventually become crystal clear glass. Fine silica sand forms the largest portion of the mixture, providing the silicon dioxide needed for the finished product. Soda ash lowers the temperature required to melt the sand, making continuous production far more practical, while limestone strengthens the finished glass and improves its long-term durability. Depending on the style of marble being produced, additional minerals and carefully prepared colorants are stored in separate hoppers waiting for later stages. Every ingredient passes through automated weighing systems, capable of measuring enormous quantities with exceptional accuracy before traveling toward industrial mixers. Inside the blending equipment, wide ribbon paddles continuously fold the dry ingredients together until the entire batch becomes completely uniform. The powders flow almost like liquid as they tumble from one end of the mixer to the other, leaving no visible separation between sand, soda ash, limestone, or the smaller mineral additions. Consistency at this stage is essential because even slight variations would become far more noticeable once the mixture enters the furnace. When computerized controls confirm the correct composition, enclosed conveyor systems transport the blended material toward one of the hottest environments anywhere inside the factory. Towering glass furnaces operate continuously, often for years without shutting down. The blended raw materials enter gradually through automated charging systems, disappearing into an intense chamber where temperatures rise well above 1,400 degrees Celsius. At first, the ingredients remain recognizable as individual particles, but within minutes, the heat begins breaking apart their original structure. The sand softens, soda ash reacts with silica, limestone decomposes, and everything gradually combines into one glowing liquid mass. Powerful burners maintain remarkably stable temperatures throughout the furnace, while the molten glass moves slowly through carefully designed channels. Hidden beneath the brilliant orange glow, thousands of tiny chemical reactions continue eliminating the boundaries between the original ingredients until only perfectly molten glass remains. Even after the mixture has melted completely, it still cannot move directly toward marble production. Tiny gas bubbles generated during melting remain suspended throughout the liquid glass. And if left untouched, they would become visible imperfections inside the finished product. To solve this, the molten glass spends additional time inside refining zones, where carefully controlled temperatures allow trapped gases to rise naturally toward the surface. The glowing liquid appears calm from above, yet microscopic bubbles are continuously escaping while the glass becomes increasingly clear. This refining stage quietly determines the optical quality that will later allow light to travel cleanly through every marble. Once refining has been completed, the molten glass begins flowing through insulated forehearth channels leading away from the furnace. These channels do much more than transport the material. They gradually reduce its temperature until the viscosity reaches exactly the level required for forming. Glass that remains too hot flows uncontrollably, while glass that cools too much becomes too stiff to shape consistently. Temperature sensors positioned throughout the forehearth constantly communicate with automated controls that adjust heating elements in real time, ensuring every section of glass reaches the forming equipment under nearly identical conditions. Now another stream of molten glass joins the process. Separate furnaces or color feeders prepare vividly colored glass using carefully measured metal oxides and mineral pigments. Cobalt compounds produce brilliant blues. Chromium creates greens. Selenium and cadmium formulations generate reds and oranges, while countless other combinations create the rich palette used inside decorative marbles. These colored streams remain completely molten as they travel toward the clear glass flow, setting the stage for one of the most visually fascinating moments in the factory. Instead of mixing the colors completely into the clear glass, precision feeding systems inject narrow streams of colored, molten glass directly into the larger flow. The different colors stretch and fold naturally as both materials continue moving together without fully blending. Depending on the arrangement of the feeders, the glass develops ribbons, spirals, flames, cat's eye patterns, or intricate swirls running through its interior. Every movement inside the flowing stream influences the final appearance. Tiny adjustments to feeder position or flow rate can dramatically alter the patterns trapped forever inside each marble. Although the glass still resembles one continuous glowing ribbon, countless unique designs are already beginning to form. The patterned molten glass now reaches the marble forming machine. Instead of pouring into individual molds, the glass exits through carefully engineered openings as continuous cylindrical streams. Rotating cutting mechanisms positioned beneath the outlets divide the flowing glass into precisely measured gobs, each containing just enough material to produce one finished marble. Timing here is extraordinary. Every cut must occur while the glass remains soft enough to shape but consistent enough to maintain identical volume from piece to piece. As each glowing gob separates, gravity carries it immediately toward the next transformation. The freshly cut glass pieces fall onto rapidly rotating grooved rollers arranged in matched pairs. This stage almost seems magical. As every glowing gob lands inside the moving grooves, continuous rolling motion begins rounding it automatically. The glass rotates rapidly in every direction, while surface tension naturally encourages it toward a perfect sphere. Unlike machining metal into a ball, the factory relies heavily on the physical properties of molten glass itself. Every rotation smooths tiny irregularities while preserving the intricate, colored patterns already suspended inside. Within only a few seconds, rough glowing pieces become nearly flawless spheres rolling steadily toward the cooling system. Although the marbles now have their final shape, they remain far too hot to handle. If allowed to cool too quickly, enormous internal stresses would develop throughout the glass, making the marbles surprisingly fragile despite their hard appearance. Instead, every sphere enters a long annealing oven designed specifically to remove those stresses. The marbles travel slowly through zones where temperature decreases almost imperceptibly over an extended period. Inside the annealing layer, the glass gradually relaxes, while internal molecular movement redistributes residual stress evenly throughout every sphere. Nothing dramatic appears to happen while the marbles move through this tunnel, yet this quiet thermal treatment determines whether they will survive impacts for decades or crack unexpectedly after leaving the factory. When the marbles finally emerge from the annealing oven, they have cooled completely to room temperature while retaining exceptional strength. Conveyor belts transfer them toward cleaning systems, where any remaining traces of furnace residue or handling marks are removed. Soft rotating brushes, filtered water sprays, and carefully controlled drying equipment restore complete clarity to every surface. For transparent marbles, this stage reveals the intricate internal patterns that have been hidden behind slight surface haze since forming. Swirls, ribbons, flames, and colored cores suddenly appear with remarkable sharpness. Even now, the manufacturing process is not complete. The cleaned marbles enter large polishing drums lined with carefully selected polishing media. As the drums rotate slowly, thousands of marbles gently roll against both the polishing material and one another. Minute surface imperfections gradually disappear while the glass develops its familiar brilliant luster. The polishing stage removes almost immeasurable amounts of material, yet the visual difference becomes immediately obvious. Light begins, reflecting cleanly across every surface, giving each marble the deep, glossy appearance associated with high-quality glass. Adidas soccer balls spin beneath enormous hydraulic presses as layers of synthetic material fuse together under carefully controlled heat and pressure, transforming flexible sheets into panels strong enough to survive thousands of powerful impacts. The press opens only seconds later, revealing perfectly formed pieces that look deceptively simple. Yet every curve, every texture, and every fraction of a millimeter has already been engineered for what comes next. Those flat panels are still nowhere close to becoming a finished ball. Before a single kick could ever send one soaring through the air, the factory must build an internal structure capable of maintaining its shape through relentless compression, and that hidden construction begins long before the outer shell is ever assembled. Production starts with large rolls of synthetic polyurethane material arriving at automated unwinding stations. Unlike natural leather used decades ago, modern performance soccer balls rely on multi-layer composites engineered for durability, water resistance, flexibility, and consistent flight characteristics. Each roll feeds into precision laminating equipment where several functional layers are bonded together into one continuous sheet. Beneath the visible outer surface, textile reinforcement fabrics, polymer foams, and adhesive films combine into a structure that balances softness with remarkable strength. Heated rollers compress every layer together while maintaining identical thickness across the full width of the material, ensuring every future panel behaves exactly like the next. As the laminated sheets move forward, another operation quietly prepares one of the ball's most important characteristics. Embossing rollers covered in microscopic surface patterns press against the material, creating thousands of tiny textures across every panel. Some patterns consist of shallow dimples, while others use intricate geometric shapes depending on the ball's intended performance. These textures influence how air flows across the finished ball during flight, helping stabilize movement while also improving grip. Although the changes appear subtle, the surface geometry created here plays an important role long after the ball leaves the factory. The embossed sheets now approach high-speed cutting systems equipped with hardened steel dies. Instead of simply producing circles or squares, these presses stamp out precisely engineered panel shapes that fit together with extraordinary accuracy. Depending on the model, the dies create traditional pentagons and hexagons, or more advanced panel geometries designed specifically for modern aerodynamic performance. Every stroke of the press produces another complete set, while computerized positioning systems minimize waste between adjacent cuts. Scrap material never remains unused for long. Recovery systems collect it automatically before directing it toward recycling processes where it can contribute to future production. Once separated, the panels travel toward printing stations that transform the plain synthetic surface into the instantly recognizable appearance associated with premium soccer balls. Large format industrial printing equipment applies graphics, logos, registration marks, and intricate color designs with remarkable precision. Some production lines use advanced digital printing, while others rely on multi-stage screen printing depending on design complexity. Between each color application, controlled drying systems stabilize the inks before the next layer arrives. What began as plain white synthetic material gradually develops into vivid geometric artwork that wraps seamlessly across the finished sphere. The printed panels continue into inspection systems, where high-resolution cameras examine every piece individually. Color consistency, print, alignment, dimensions, surface texture, and edge quality are verified automatically before the panels move onward. Pieces showing incomplete printing, dimensional variation, or surface defects are diverted immediately without interrupting the production flow. Only perfectly formed panels continue toward assembly, because even minor inconsistencies become much more noticeable once the ball takes shape. While the outer shell components move through inspection, another production line prepares the internal bladder that gives the ball its elasticity. High-grade butyl or natural latex compounds begin as carefully blended rubber mixtures prepared inside enclosed mixing equipment. Massive internal mixers knead the rubber under controlled temperatures until every ingredient disperses evenly throughout the compound. Carbon black, stabilizers, curing agents, and elastic polymers all contribute specific mechanical properties, ensuring the finished bladder retains air efficiently while remaining flexible through repeated inflation and impact. The rubber compound leaves the mixers and passes through extrusion equipment, where it forms continuous tubes of carefully controlled thickness. Sections are cut automatically before entering heated molds that shape them into hollow spherical bladders. Inside the molds, heat and pressure initiate vulcanization, permanently cross-linking the rubber molecules into an elastic structure capable of expanding repeatedly without permanent deformation. Once curing finishes, the bladders cool gradually before inflation valves are installed through precision insertion equipment. Every bladder receives an initial inflation test immediately afterward to verify airtight performance before continuing. Now, two completely separate manufacturing streams finally begin moving toward one another. The finished bladder enters temporary inflation stations, where compressed air gives it enough shape to support shell assembly. Nearby, workers or automated positioning systems begin arranging the printed outer panels around the inflated core according to the exact geometric layout required for the finished ball. Although the synthetic shell appears flat only moments earlier, each panel now starts curving naturally as it wraps around the expanding bladder. Depending on the production method, assembly follows one of two highly engineered paths. For thermally bonded premium balls, precisely positioned panels enter specialized molding systems, where heat-activated adhesives permanently fuse adjoining edges together. Hydraulic molds surround the partially assembled ball, while carefully controlled temperature and pressure activate the bonding layers hidden beneath the outer surface. Rather than relying on visible stitching, the panels become one continuous, waterproof shell with exceptionally smooth seams. This process creates remarkable dimensional consistency while reducing water absorption during play. For stitched models, automated pre-punching equipment prepares every panel edge before high-strength polyester threads begin joining neighboring sections. The stitching sequence follows a carefully planned order that gradually encloses the inflated bladder inside the growing shell. Each stitch must maintain consistent tension throughout the ball, because uneven stitching could alter both shape and durability. The final seam closes only after the bladder has been fully enclosed, completing the spherical structure for the first time. Although the ball now looks finished, another major transformation still waits ahead. Every assembled ball enters calibration stations where controlled inflation raises internal pressure to its specified level. Precision gauges monitor air pressure continuously, while rotating support systems keep the ball perfectly centered throughout testing. The shell stretches slightly as pressure increases, allowing every panel to settle into its final position. Tiny adjustments made here influence how uniformly the ball responds when struck at high speed. The inflated balls continue into heated shaping molds that perform one final geometric correction. Even carefully assembled panels may contain microscopic variations before molding. Inside the shaping press, heat and pressure gently encourage every seam and panel to conform to the exact spherical dimensions programmed by the manufacturer. When the molds open again, each ball displays remarkably consistent diameter and roundness, creating the foundation for predictable flight characteristics. Now the quality control process becomes especially demanding. Every ball rolls individually beneath laser measurement systems capable of detecting extremely small deviations in circumference, roundness, and panel alignment. Computer-controlled cameras inspect print registration from multiple angles, while automated rotation allows every section of the surface to be examined. Balls showing dimensional irregularities, cosmetic defects, or seam inconsistencies leave the production line automatically. Those meeting specification continue toward another series of demanding evaluations. Impact testing begins inside mechanical kicking machines where pneumatic launch systems repeatedly strike inflated balls with carefully controlled force. Some machines fire the balls against rigid surfaces hundreds or even thousands of times, while sensors monitor rebound behavior and structural stability. Nearby compression equipment repeatedly squeezes other samples to simulate extended play. Additional pressure testing stations monitor long-term air retention, ensuring the bladder and valve continue performing after repeated impacts. Only after surviving these evaluations does production move toward its final stages. Accepted balls pass through cleaning stations where soft rotating brushes remove any remaining manufacturing residue from the outer surface. Gentle polishing systems restore a uniform finish while preserving the embossed texture created much earlier during lamination. Bright inspection lighting reveals the completed appearance for the first time, allowing automated cameras to perform one final visual verification before packaging begins. Packaging starts as automatic deflation equipment reduces internal pressure slightly, allowing the balls to occupy less space during transportation while protecting the shell from unnecessary stress. Depending on the retail format, some models remain partially inflated while others are folded gently into compact packaging. Printed cartons, protective bags, or display boxes arrive from parallel packaging lines where robotic loading systems position every ball precisely inside. Instruction leaflets, inflation information, and identification labels are added automatically before the packages are sealed. Completed retail packages continue towards secondary packaging where corrugated shipping cartons open automatically from flat blanks. Robotic handling equipment loads the programmed number of packaged soccer balls into every carton before folding mechanisms close the upper flaps. Hot melt adhesive secures each seam while compression conveyors maintain square geometry until the adhesive cures completely. Machine vision confirms carton integrity, product count, and coding before every case advances toward the warehouse. Louisville Slugger baseball bats begin spinning at astonishing speed inside computer-controlled lathes as rough wooden billets blur into smooth cylinders with every pass of the cutting tools. Thin ribbons of maple or ash peel away continuously, collecting beneath the machines, while the bat's familiar profile slowly emerges from what only moments earlier looked like an ordinary block of timber. Even now, however, the bat is still far from complete. The balanced barrel, the precisely tapered handle, and the reinforced striking surface all depend on dozens of tightly controlled manufacturing stages that started long before the first billet ever reached a cutting machine. The process begins deep inside lumber yards, where carefully selected hardwood logs arrive after harvesting. For premium wooden bats, maple, ash, or birch are the most common choices because each species offers a unique balance of density, flexibility, and impact resistance. Massive scanning systems evaluate every log before processing begins, measuring diameter, straightness, and internal consistency. Advanced imaging equipment helps identify defects hidden beneath the bark, allowing sections with knots, irregular grain, or structural imperfections to be removed before they ever reach production. Only the cleanest portions continue toward the sawmill, where the first major transformation takes place. Gigantic bandsaws divide each log into long rectangular planks, while automated conveyors carry every board through additional optimization scanners. These systems examine grain orientation with remarkable precision because the direction of the wood fibers has an enormous influence on how the finished bat behaves under repeated impacts. Computer-controlled cutting equipment then divides the selected boards into shorter rectangular blocks known as billets. Each billet already contains enough material for one future baseball bat, although at this stage it still resembles nothing more than a smooth wooden beam with sharp square edges. Freshly cut billets cannot move directly towards shaping. Wood naturally contains moisture that varies throughout the log, and if left untreated, it could cause the finished bat to warp, shrink, or change weight over time. Instead, the billets enter enormous drying kilns, where carefully controlled heat, airflow, and humidity slowly reduce moisture content over several days or even weeks, depending on the species. Large circulation fans move conditioned air continuously through tightly stacked rows of timber, while computerized control systems constantly adjust temperature and humidity. The drying process happens gradually because removing moisture too quickly could introduce internal stresses or surface cracks long before the bat ever reaches the field. Once drying is complete, every billet returns to another inspection stage. Moisture meters verify internal water content, while scanners once again evaluate grain quality. Workers and automated systems both examine the wood, rejecting any billet showing hidden splits, discoloration, or fiber irregularities revealed during drying. The remaining billets continue toward precision weighing stations, where every piece is categorized according to density. This sorting stage allows manufacturers to match specific wood characteristics with different bat models, ensuring the finished product reaches its intended balance and swing weight. Now the rectangular billets finally approach the lathes introduced at the beginning of the journey. Robotic loading systems position every billet securely between rotating centers before powerful electric motors accelerate the wood to high rotational speed. Computer-guided cutting heads begin removing material in carefully programmed passes. Rather than carving the final shape immediately, the machines gradually reduce the billet through multiple stages. Each pass removes only a thin layer, allowing remarkable dimensional accuracy while preserving a smooth surface. Slowly, the square timber transforms into a perfectly cylindrical blank before the recognizable taper of the bat begins appearing. As the cutting tools continue moving along the spinning wood, the thick barrel develops first. Further down the blank, the profile narrows steadily into the handle before widening slightly again at the knob. Every contour follows digital specifications accurate to fractions of a millimeter. Laser measuring systems positioned beside the lathes monitor dimensions continuously, while automatic corrections compensate for even tiny variations in cutting tool wear. What appears to be a simple wooden club is actually the product of highly controlled machining where balance, weight distribution, and geometry are engineered with extraordinary precision. The freshly turned bat still carries fine machining marks left by the cutting tools. so it immediately enters sanding stations designed to refine every surface. Wide abrasive belts and rotating sanding heads glide smoothly across the spinning wood, removing microscopic imperfections without altering the carefully machined profile. The sanding sequence progresses through increasingly finer abrasives until the entire bat develops an exceptionally smooth finish. Fine wood dust is extracted continuously through high-powered vacuum systems, keeping the cutting surfaces clean while preventing dust from settling back onto the product. Although the bat already feels smooth, another critical process now begins. Branding and identification markings are applied through laser engraving or precision stamping systems depending on the production method. Logos, model numbers, wood species, and manufacturing information are positioned accurately along the barrel before permanent markings are burned or pressed into the surface. This stage also establishes the preferred hitting orientation for many wooden bats by identifying the optimal grain alignment. Those markings later help players strike the ball using the stronger side of the bat's grain structure. Before any finish is applied, every bat undergoes another detailed inspection. Operators rotate the bat beneath bright lighting, while optical systems examine the grain from end to end. Straight, uninterrupted grain lines are especially important for premium models because they contribute significantly to impact performance and durability. Even minor surface defects that escaped earlier inspections become much easier to detect after machining and sanding. Only bats meeting strict visual and dimensional standards continue toward finishing. Now the wood begins receiving the protective coatings that give many baseball bats their rich appearance. Depending on the model, automated spray systems apply stains ranging from natural clear finishes to deep black, rich brown, cherry, or other colors. Each coating settles evenly across the sanded surface, while the bats rotate slowly to eliminate runs or uneven coverage. After staining, the bats enter drying tunnels where carefully controlled airflow allows solvents to evaporate gradually without disturbing the finish. The grain pattern becomes dramatically more visible beneath the transparent coatings, revealing the natural character hidden inside the wood. Once the stain has cured, clear protective top coats are applied through another series of automated spray booths. Multiple thin layers build gradually instead of relying on one heavy application. Each coat protects the wood from moisture while producing the smooth finish associated with professional quality bats. Between coats, the bats travel through curing tunnels, where temperature and airflow remain tightly controlled. Every additional layer increases durability while preserving the natural balance engineered during machining. Some models receive additional surface polishing after the final clear coat cures. Soft polishing wheels rotate gently against the barrel and handle, producing a consistent satin or gloss appearance depending on the intended finish. The polishing stage removes tiny dust particles or surface irregularities that may have settled during curing while creating an exceptionally smooth feel in the player's hands. Weight and balance testing now become the primary focus. Every finished bat passes across highly accurate electronic scales that verify total weight before specialized balancing equipment measures the distribution of mass along its length. Even two bats sharing identical dimensions can feel very different if weight distribution changes slightly. Manufacturers therefore compare each bat against strict balance specifications, ensuring the finished product delivers the swing characteristics expected for that model. Pepsi cans lock shut under a double seaming head, while the cola inside is still cold, pressurized, and fizzing against the lid. A filled aluminum can enters the seamer through a star wheel. The can body is open at the top, and the carbonated Pepsi sits just below the rim with a controlled headspace above it. A lid drops onto the can flange. The seaming chuck holds it in place. Rollers move in with precise pressure, curling the lid edge and can flange together into a tight double seam. The first roller forms the metal. The second roller compresses it. The seam becomes a folded mechanical lock that holds carbonation without glue. The can leaves the seamer sealed, rigid, and ready for inspection. Inside, dissolved carbon dioxide remains trapped under pressure. Before the can reaches the seamer, it is filled in a rotary pressure filler. Empty cans move into the filler after rinsing. They are spaced by star wheels and carried around a circular filling bowl. Each can rises under a valve. The valve controls liquid flow, so the carbonated drink enters quickly without excessive foam. The Pepsi stream is cold at this point. Cold liquid holds carbon dioxide more efficiently and behaves more calmly during filling. The dark cola enters the can in a controlled flow. The level rises with fine bubbles moving upward through the liquid. When the programmed fill height is reached, the valve closes and the can moves immediately toward the lid feeder. The filler must work with speed and restraint at the same time. Carbonated liquid wants to release gas when pressure changes. The filling valve shapes the flow to reduce splashing. The short transfer from filler to seamer prevents gas loss before closure. The carbonated beverage arrives at the filler through closed stainless steel pipework. The line remains pressurized and smooth. Sharp turns and sudden pressure drops are avoided. The liquid moves from the carbonator to the filling bowl without open exposure. Inside the carbonator, chilled flat Pepsi receives carbon dioxide. The liquid enters through a controlled feed line. Carbon dioxide enters under pressure through diffusers or contact surfaces. The gas breaks into fine bubbles and dissolves into the cola. The system controls pressure, liquid temperature, and gas flow, so every batch reaches the target carbonation level. The beverage is chilled before carbonation. It passes through a plate heat exchanger, where thin stainless steel plates separate the cola from a cold circulating fluid. Heat leaves the beverage rapidly. The liquid exits cold, dense, and ready to absorb gas. Some lines remove dissolved air before carbonation. In a deaeration unit, the flat drink moves under reduced pressure. Tiny air bubbles separate from the liquid and are pulled away. This makes carbonation more consistent and helps the drink hold its sparkle after sealing. The flat Pepsi comes from a blending system. Treated water and concentrated syrup meet at a proportioner. The syrup line is dark, sweet, and strong. The water line is clear and neutral. Flow meters measure both streams, and automatic valves adjust the ratio continuously. As the two streams combine, the syrup thins into finished strength cola. The color remains deep brown, but the flavor, sweetness, acidity, and body shift into the final beverage balance. This flat cola moves directly toward chilling, deaeration, and carbonation. The syrup is made in a separate syrup room. Treated water enters a stainless steel mixing tank. Sweetener is added first. It may arrive as liquid sweetener or as sugar dissolved into the water. The tank agitator keeps the base moving so no dense layer forms at the bottom. When sugar crystals are used, they fall into the water and gradually disappear. The mixture becomes heavier and glossy as the solids dissolve. Recirculation pumps may draw syrup from the bottom and return it near the top, creating a uniform sweet base. The sweet base passes through filtration before flavoring. Fine screens or filters remove undissolved material. Clean syrup protects proportioning valves, pumps, and filling equipment later in the process. Pepsi concentrate then enters through a closed dosing line. Caramel color spreads through the sweet base. Acids and flavor components blend into the liquid. The tank changes from clear syrup into a dark cola concentrate. The agitator turns steadily until the batch is uniform from the surface to the outlet. The finished syrup is much stronger than the drink itself. It is held in a tank with slow agitation. Pumps send it forward only as the proportioner requires it. The syrup flow and treated water flow create the finished cola continuously during production. The treated water begins as incoming plant water. It moves first through particulate filtration to remove suspended solids. It then passes through activated carbon, which reduces unwanted taste and odor. Additional polishing steps create a consistent water base for syrup making and final blending. This water matters because it makes up most of the beverage. Its clarity, taste, and mineral balance must stay steady. Sensors monitor flow, pressure, and treatment performance before the water enters storage tanks. While the liquid side is prepared, containers move through their own system. Aluminum cans arrive empty, lightweight, and open at the top. They are already formed and printed before entering the filling hall. The cans feed from depalletizers into single-file lanes. Air conveyors and guide rails control their movement without crushing the thin walls. Before filling, the cans are rinsed. They invert, receive a blast of filtered air or treated rinse water, drain, and return upright. This removes loose particles from the interior before the cola enters. PET bottles follow another route. They often begin as preforms. A preform is a short, thick plastic tube with a finished threaded neck. The body has not yet been expanded. The preforms enter a heating oven and rotate beneath infrared lamps so the plastic warms evenly. A heated preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center, pulling the softened plastic lengthwise. Compressed air then expands it outward until it touches the chilled mold walls. The base, shoulders, sidewall, and label panel form at once. The mold opens and the empty bottle exits by its neck ring. Air conveyors carry it forward. Because the bottle is light before filling, air jets can push it along while rails support the neck finish. The bottles pass through rinsing before filling. Each bottle is gripped, inverted, cleaned internally, drained, and returned upright. It then enters a pressure filler similar in purpose to the can filler, but matched to bottle geometry. For plastic bottles, the filling valve seals around the mouth. Pressure is balanced before liquid enters. Pepsi flows into the bottle with controlled turbulence. The fill level rises to the target height, and the valve closes. The filled bottle moves immediately to capping. Caps are sorted in an orienting bowl and sent down chutes to the capping heads. Each cap lands on the bottleneck and tightens to a controlled torque. The tamper band locks below the neck ring as the cap finishes turning. Glass bottles use a heavier container path. They pass through inspection before filling. Cameras and light systems check the mouth, base, sidewall, and interior. After filling, crown caps or threaded closures seal the bottle. The closure must hold carbonation pressure as the beverage warms and moves through packing. Every sealed container enters inspection. Fill level sensors check the liquid amount. Cameras inspect caps, can seams, bottle shapes, crown placement, dents, thread finish, and printed decoration. Any defective unit is removed automatically from the conveyor. Filled containers are often wet on the outside because the beverage is cold. Air knives remove condensation. Thin, high-speed sheets of air strike the cans and bottles from multiple angles. Droplets break away from lids, seams, shoulders, labels, and bases. M&M's pieces gain their hard candy shells through repeated polishing, coloring, and drying cycles inside large rotating pans. The chocolate centers arrive at this stage as small, rounded cores. They are already formed, cooled, and firm enough to tumble without flattening. The centers enter wide coating pans that rotate at a steady angle. As the pan turns, the centers climb up the inner wall, slide back down, and roll over each other in a continuous shifting bed. A sugar syrup is added in very thin amounts. It does not pour in heavily. It enters as a controlled stream or fine spray. The syrup touches the moving centers and spreads across their surfaces. Drying air flows through the pan, removing moisture from that layer. The syrup hardens into a thin shell. The cycle repeats again and again. A small dose of syrup coats the centers. The pieces tumble. Air dries the surface. Another dose follows. Each layer adds thickness. The round centers gradually become slightly larger, smoother, and stronger. This is how the shell is built, not in one thick coat, but in many thin, hardened layers. At first, the shell is plain and pale. Later, color is added to separate batches. Red pieces receive red syrup. Yellow pieces receive yellow syrup. Blue, green, orange, and brown batches move through their own color systems. Each color must remain separate until blending, because the coating pans create one color at a time. The pan speed controls the shape. If the movement is too slow, pieces may stick together or develop flat spots. If it is too fast, they can chip or bounce unevenly. The pan turns just enough to keep the candy rolling smoothly while the coating dries. Drying air is just as important as syrup. If the air is too weak, the pieces stay wet and clump. If it is too aggressive, the surface can roughen or dry before the coating spreads. Air temperature, humidity, and flow rate are balanced so the shell becomes hard, even, and glossy. Before these coating pans receive the centers, the chocolate cores are made in a separate process. Chocolate mass begins with cocoa ingredients, sugar, milk ingredients, cocoa butter, and fats blended into a thick paste. The paste passes through refining rollers that reduce the particle size. Sugar crystals, cocoa particles, and milk solids become fine enough that the finished chocolate feels smooth instead of gritty. The refined chocolate enters conching equipment. Heavy mixing arms work the chocolate under controlled heat. The mass becomes more fluid as fat spreads around the tiny particles. The texture becomes smoother, and the chocolate develops the flow needed for forming centers. The chocolate then moves into tempering. Tempering controls the cocoa butter crystals inside the chocolate. The liquid chocolate is cooled and gently reheated through specific temperature stages. This gives the chocolate the ability to set firm and resist smearing during later coating. To form the centers, tempered chocolate is deposited into small molds or dropped in measured portions onto a cooling surface, depending on the product type. For classic milk chocolate M&Ms, the goal is a small, lentil-shaped center. The chocolate must settle into a rounded disc that is thick in the middle and thinner at the edges. The formed centers pass through cooling tunnels. Cold air removes heat, and the chocolate solidifies. The centers contract slightly as they set. Once firm, they release from molds or separate from the forming surface. They are then screened to remove broken pieces, doubles, or misshapen centers. Some M&M's varieties need a different center. Peanut M&M's begin with roasted peanuts. The peanuts are cleaned, sized, and roasted until their moisture drops and their texture becomes crisp. After cooling, they are coated with chocolate before shell building begins. Each peanut becomes the center around which chocolate and candy layers are added. Peanut butter centers use a prepared paste. Ground peanuts, sweetener, fat, and stabilizing ingredients are mixed until thick and smooth. The paste is formed into small cores, chilled, and coated with chocolate or candy layers depending on the line. Pretzel or crispy varieties use baked centers that must remain dry and strong before coating. For the classic chocolate type, the cooled chocolate centers are transferred toward the panning room. The centers are loaded into the coating pans by measured batch weight. The pans begin rotating and the first shell building layers are applied. A base syrup layer helps seal the chocolate. This prevents color syrup from interacting directly with the chocolate surface. The early layers also strengthen the center so it can tolerate many more coating cycles. The pieces are repeatedly wetted and dried until the shell reaches the required thickness. The surface becomes harder with each cycle. When enough base shell is built, color coding begins. Colored syrup layers add brightness and identity to the candy. Each batch continues tumbling until the color is even. The pieces must not show pale spots, streaks, or exposed base layers. The rolling action distributes syrup across the top, bottom, and edges of every piece. Because each candy is small and constantly moving, the final shell becomes smooth and rounded. After coloring, the pieces move into polishing. A polishing solution is added in tiny amounts while the candy tumbles. The surface becomes brighter and glossier. Friction between the pieces helps smooth microscopic roughness. The candy changes from matte-colored pellets into shiny finished M and M's. The polished candies are discharged and cooled. They move through screens that separate out small fragments, oversized clusters, chipped pieces, and dust. The accepted pieces continue by color into holding bins. The white letter is added after the shell is complete. The candies move into a printing system that orients and contacts the pieces quickly. A food-grade white marking material is transferred onto one side of each candy. The printing mechanism must apply the mark without cracking the shell or smearing the surface. Because M&Ms are rounded and small, perfect orientation is difficult. The system uses controlled feeding, vibration, and contact printing to mark the moving pieces at high speed. The printed candies pass through a short drying section, so the letter sets before blending and packaging. Different colors are then blended. Each color stream feeds from its own hopper. Vibrating feeders meter red, yellow, green, blue, orange, and brown pieces into a common conveyor or blending drum. The ratios are controlled so each finished package receives a balanced mix. The blending must be gentle. The shells are hard, but they can still chip if dropped too far or crushed between equipment surfaces. Conveyors, chutes, and drums are shaped to keep the pieces moving smoothly. The mixed candies enter the weighing system. For small bags, a multi-head weigher divides the candy into several weigh buckets. Each bucket holds a small portion. The machine calculates which bucket combination equals the target weight, then releases those portions together. The selected candy drops into the bagging machine. Printed film unwinds from a roll and moves around a forming tube. The film edges meet and seal vertically, creating a tube. The candy falls through the tube into the open package. Horizontal sealing jaws close the bottom of one package and the top of the previous one. The jaws also cut the packages apart. Each bag leaves sealed, filled, and separated from the film web. For larger stand-up pouches, film is formed with gussets that allow the bag to stand. The pouch is filled by weight, sealed at the top, and cooled at the seal area so the closure holds cleanly. Resealable formats receive a zipper strip integrated into the film before the top seal is completed. For small tubes, cartons, or theater boxes, the packaging path changes. Paperboard blanks open into box shapes. Candy is weighed or volumetrically metered into each carton. Flaps fold in sequence and lock or glue shut. The package then moves through inspection and coding. For bulk formats, candies are filled into larger bags or tubs. The filling system uses wider chutes and heavier weighing equipment. The same controls apply correct weight, clean closure, shell protection, and consistent color blend. Every package passes through inspection. Check weighers verify that the amount of candy is within the target range. Metal detectors scan the package. Vision systems check seal quality, print alignment, code presence, bag shape, and carton closure. Coding equipment applies production information to the bag, pouch, carton, or outer case. Inkjet or laser systems print while the package moves on the conveyor. A scanner can confirm that the code is readable. Accepted retail packs move into secondary packing. Bags may be counted and loaded into display cartons. Cartons may be grouped into corrugated cases. A case former opens a flat blank or folded case, seals the bottom, and presents it for loading. Mechanical pushers or pick-and-place systems load the retail packs into the case. The arrangement depends on package shape. Flexible bags need gentle compression. Boxes stack more tightly. Pouches may stand upright or lay flat in rows. Skittles centers are cut from a thick, fruit-flavored candy rope before their colored shells are built around them. The center mass starts as a chewy sugar base. Sugar, glucose syrup, and water are cooked together until the mixture reaches the correct solids level. Heat drives away moisture, and the syrup becomes dense, clear, and heavy. The cooked syrup is not yet a finished candy. It is a hot, elastic base that needs acid, flavor, color preparation, cooling, and forming. The hot candy mass moves onto a cooling table or through a continuous cooling system. As it cools, it becomes thicker and more workable. Acid ingredients and fruit flavor components are added while the mass is still soft enough to fold. The mixing action pulls the flavor through the candy until every section has the same sharp fruit profile. The base must stay pliable. If it cools too far, it becomes difficult to shape. If it stays too warm, it stretches too much and will not cut cleanly. Temperature controls the entire forming stage. The candy mass is worked into a long rope. Rollers and forming wheels pull it forward and reduce its diameter. The rope becomes smooth, rounded, and even. Inside, the candy is dense and chewy. Outside, the surface firms just enough to hold shape. The rope enters a cutting machine. Rotating knives or forming dies divide it into small pillow-shaped centers. Each cut creates a soft pellet with rounded edges. The pieces are still not shiny, hard, or fully colored like finished Skittles. They are chewy cores waiting for shell coating. The cut centers move on to cooling conveyors. Air removes heat and firms the surface. The centers must become strong enough to tumble in coating pans without sticking together or deforming. They remain chewy inside, but the outside develops enough firmness for panning. The centers pass through sizing screens. Pieces that are too small fall away. Oversized pieces and doubles are removed. Correct size centers continue toward the coating area. The sorting step helps the finished candy feel consistent, even though millions of pieces move through the line. The accepted centers enter large rotating coating pans. These pans are wide, smooth, and tilted. As each pan turns, the centers climb the inner wall, then roll back down over one another. This tumbling motion exposes every surface repeatedly. A sugar syrup is prepared separately for shell building. Sugar, glucose syrup, water, color, and other coating ingredients are cooked and held at a controlled temperature. The syrup must flow through spray nozzles, but it must also dry into a hard shell once applied. The first shell layers are usually built gradually. A small amount of syrup is added to the tumbling centers. The syrup spreads across the surface. Drying air flows into the pan and removes moisture. The thin layer hardens. Then another small amount is added. The shell forms through repetition. Spray, tumble, dry. Spray, tumble, dry. Each cycle adds a little thickness. The pieces become stronger and smoother with each pass. The centers stay chewy while the outside begins developing a crisp sugar shell. The pan speed must be carefully controlled. Slow tumbling can cause clumping and flat spots. Fast tumbling can chip the growing shells. The best motion keeps the pieces rolling continuously, with a dry rattling sound as the shell hardens. Drying air is adjusted for temperature and humidity. If the air dries the syrup too slowly, pieces stick together. If it dries too fast, the surface can become rough. The coating layer must spread before it sets, then crystallize evenly. Each flavor color batch is handled separately. Lemon pieces receive yellow coating. Orange pieces receive orange coating. Strawberry, grape, lime, green apple, or other flavors receive their own colors depending on the product version. The fruit center and outer color must match the intended final mix. As the coating builds, the pieces change from soft pellets into bright candy buttons. They become smoother and rounder, but they keep a slight flattened oval shape. The shell grows thick enough to give the first crisp bite before the chewy center begins. After the main color coating is finished, polishing begins. A very small amount of polishing solution is added while the candy continues tumbling. Friction between pieces smooths the surface. The candies become glossier. The shell shifts from dull color to bright shine. The polished Skittles leave the coating pans and move onto cooling and drying conveyors. The shell must stabilize before printing. If the surface remains tacky, the printed mark can smear. If the shell is too brittle or dusty, the print will not transfer cleanly. The pieces pass through screens and air separators. Loose sugar dust, broken fragments, and clusters are removed. The accepted candies move into color-specific holding bins. Each bin holds one finished color and flavor. The white S is applied in a printing stage. Candies feed from hoppers into channels or pockets that position them for contact with printing equipment. A food-grade white marking material transfers onto the shell surface. The equipment touches each candy briefly, leaving the letter without cracking the shell. Printing small rounded candies is difficult because each piece can land at a different angle. The feeding system uses vibration, channels, and controlled flow to improve orientation. Not every motion is forceful. The candy must move fast, but the shell surface must remain intact. After printing, the candies pass through a short drying section. Air sets the printed mark so it does not smear during blending. The pieces now have the full outside appearance: bright shell, glossy surface, and white printed letter. Blending happens after colors are finished and printed. Each color feeds from its own hopper. Vibrating feeders release measured amounts onto a common conveyor or into a blending drum. The system controls the ratio, so the finished bag receives the intended color mix. The blending motion must be gentle. Skittles shells are hard, but they can chip if dropped from high distances or squeezed under heavy pressure. Chutes are curved. Conveyors are controlled. The candy flows like small polished stones without being crushed. The mixed candy moves toward the weighing system. A multi-head weigher handles the irregular flow. Candy feeds into many small buckets. Each bucket holds a partial amount. The machine calculates which combination of buckets equals the target pack weight. The selected buckets open together. Skittles drop into a funnel and enter the bagging machine. The fall is short and guided to prevent cracking or bouncing out of the forming tube. Packaging film unwinds from a roll. The film is printed before it reaches the machine. Registration sensors read marks on the film, so each bag is cut and sealed in the correct place. The film passes over a forming collar and wraps into a vertical tube. A vertical seal closes the back of the tube. Horizontal jaws close the bottom. The weighed candy drops into the open package. The jaws close again above the candy, forming the top seal of one bag and the bottom seal of the next. A knife cuts between seals, releasing a finished bag. The sealed bag contains a controlled amount of mixed color Skittles with enough internal space to move without crushing. The film protects the candy from moisture because humidity can dull the shell and make the surface sticky. The first movement for sardines is washing. Fresh or chilled sardines pass through rotating drums and spray channels where cold water removes loose scales, blood, and surface debris. The fish slide against stainless steel guides, turning and flashing under the water as the line separates clumps and spreads them into a steady flow. Their bodies are still whole at this point, but the factory is preparing them for a much tighter transformation. Sizing comes next. The sardines travel across grading equipment with slots, rollers, or vibrating channels that separate them by length and thickness. A can needs fish of similar size, so the pieces pack evenly and cook uniformly. Fish that are too large move to another format. Smaller fish may go to a different can size or product style. Now the line begins shaping the fish for the can. The sardines move into heading and gutting equipment. Blades or cutting wheels remove the heads. A mechanical opening system cuts the belly area and removes the internal contents. Water jets rinse the cavity immediately after cutting. The fish are no longer whole. They have become prepared bodies with clean interiors and trimmed ends. The trimming must be consistent. If too much is removed, the yield and shape are poor. If too little is removed, the fish will not pack cleanly. The machine holds the fish in channels and guides them through the blades, so every body leaves at a similar length. The cleaned sardines pass through another rinse. Water flushes away loose fragments and leaves the fish ready for salting or brining. The surface becomes cleaner and firmer. What happens next controls both texture and flavor before the fish ever reaches the can. The sardines enter a brining stage. They move through a saltwater bath or receive a controlled salt treatment. Salt begins drawing moisture from the surface and seasoning the flesh. The brine concentration and contact time must be balanced. Too little salt leaves the fish bland and soft. Too much makes the flesh harsh and dry. After brining, the sardines drain on perforated belts. Excess liquid falls away. The bodies are now slightly firmer. Their surface is ready for the first major heat step. Some canning lines pre-cook the sardines before packing. The fish pass through a steam cooker or continuous oven. Steam surrounds them, and heat moves into the flesh. The texture changes from translucent raw fish to opaque, firm cooked fish. Moisture and natural oils release from the tissue. This stage is one of the hidden turning points. If the sardines are packed raw without the correct process, too much liquid can release later inside the can. If they are pre-cooked too aggressively, the flesh becomes dry and breaks during packing. The cooker gives the fish enough firmness to handle while preserving the soft structure needed in the final can. The cooked sardines move through cooling and draining. Fans or controlled air reduce surface heat. Perforated conveyors let liquid drain away. The fish must be cool and stable enough to enter the packing station without tearing apart. Now the cans enter the process from a separate path. Empty metal cans feed from stacks or bulk depalletized trays. They move along conveyors toward cleaning and inspection. The cans are open at the top, with rolled rims ready for sealing later. Air jets remove loose particles from the interior. Guides align the cans so they arrive beneath the packing equipment in a steady rhythm. The sardines and empty cans meet at the filling section. The fish are arranged by orientation. Some lines pack them by hand-like mechanical placement, using guides and portioning devices. Other systems use semi-automatic feeders that align the fish and slide them into the can. The goal is a tight, neat arrangement with the fish lying flat or slightly nested. The packing pattern depends on the can style. In rectangular cans, sardines may be laid side by side with alternating head and tail ends to use the space efficiently. In round cans, smaller fish may curve slightly around the container. The metal walls define the final block of fish. This is where the product starts looking familiar. The fish are no longer just moving along a belt. They are becoming a compact portion inside a shallow metal container. After the fish are placed, liquid is added. The filling medium may be oil, tomato sauce, water, brine, mustard sauce, or another prepared sauce. Each liquid has its own preparation system. For oil-packed sardines, filtered oil is held in a stainless steel tank and pumped to the filler. The oil flows through nozzles into each can, filling the spaces between fish. It coats the surface and displaces air pockets. The oil level must be precise because too little leaves exposed fish, while too much interferes with sealing. For tomato sauce, a separate sauce line prepares the liquid. Tomato concentrate, water, salt, spices, and other ingredients blend in heated tanks. Agitators keep the sauce uniform. The sauce may pass through screens to remove oversized particles before filling. It must be thick enough to cling to the fish, but fluid enough to flow through nozzles. For brine-packed sardines, salt water is mixed to a controlled concentration. The brine fills the can around the fish and helps distribute seasoning through the pack. The brine must be clear, measured, and free from undissolved crystals. The liquid filler doses every can. Nozzles lower or position above the can opening and release the correct volume. The liquid creeps between fish bodies, filling narrow gaps. Air bubbles rise to the surface. The can now contains fish and medium, but it is not yet safe as a sealed product. The next stage traps the contents permanently. Before sealing, the can may pass through an exhaust or vacuum step. The goal is to remove excess air from the headspace. Heat or vacuum reduces trapped oxygen and prepares the container for a strong internal vacuum after processing. This helps the can maintain shape and reduces unwanted pressure changes during retorting. A lid is placed onto each filled can. The lid feeds from a magazine, separates one at a time, and drops onto the can body. The filled can enters the seamer. The seaming chuck holds the lid while rollers move against the rim. The first seaming operation curls the lid edge and can flange together. The second operation compresses the folds into a tight double seam. This seam is purely mechanical. Layers of metal interlock around the can edge, creating a sealed container that can withstand the heat and pressure of sterilization. Now, the most important transformation happens out of sight. The sealed cans move into retorts. These are large pressure vessels or continuous sterilizing systems designed to heat sealed cans to a controlled temperature for a controlled time. Steam, hot water, or a steam-air mixture surrounds the cans. Pressure prevents the containers from deforming while the internal contents heat. Inside each can, the sardines continue cooking. The fish soften, bones become tender. Oil or sauce moves into the spaces between the pieces. The liquid and fish exchange flavor. The can becomes a sealed cooking chamber, and the product develops its final texture. The retort cycle must be exact. Heat must penetrate to the coldest point inside the can. That point takes the longest to reach the target temperature. Time, temperature, can size, fill weight, liquid type, and product density all affect the thermal process. The system records the cycle, so each batch receives the required heat treatment. After sterilization, the cans are cooled under controlled conditions. Cold water or cooling media remove heat from the metal and product. Pressure control during cooling prevents the cans from bulging or drawing in too sharply. The contents stabilize as the temperature drops. Barilla-style pasta takes its first shape when coarse golden semolina and water are pressed into a dense dough under vacuum. The semolina does not enter like fine cake flour. It is granular, sandy, and yellow from durum wheat. It flows from storage silos through enclosed pipes and weighing systems. Screens remove oversized particles. Magnets catch stray metal fragments. The semolina drops into the mixer as a dry, rough stream that will become pasta only after hydration, pressure, shaping, and slow drying. Water enters through a metered line. The amount is small compared with bread dough. Pasta dough is intentionally stiff. It is not soft, elastic, or fluffy. It is a compact mixture built to be forced through metal dies. As water hits the semolina, the grains darken and swell. The first change is quiet but important. Dry particles begin binding into damp crumbs. The mixer turns with heavy paddles. It does not whip air into the dough. It folds the semolina and water together until the mixture becomes evenly hydrated. At this stage, the dough looks more like wet sand than a smooth mass. That rough texture is exactly what the extruder needs. The real transformation is still coming. Before extrusion, the dough passes through vacuum. air is pulled out of the mixing chamber. Tiny bubbles trapped between semolina particles disappear. This matters because air pockets would create weak spots, pale streaks, and rough breaks in the finished pasta. Under vacuum, the dough becomes denser and more uniform. Now the pressure begins. A large screw inside the extruder pushes the stiff dough forward. The screw rotates inside a barrel, compressing the mixture with every turn. The dough becomes warmer from friction and pressure, but temperature is controlled so the starch and protein do not cook. The mass moves slowly toward the die head like thick clay being forced through a narrow opening. The die decides the pasta shape. Every tube, strand, shell, twist, ribbon, and hollow form comes from the geometry of the die. The dough has no final identity until it reaches this metal plate. What enters the die as compact semolina dough exits as spaghetti, penne, macaroni, fusilli, rigatoni, or another shape. For spaghetti, the die contains many small round holes. The dough pushes through them and exits as long continuous strands. These strands drop downward in parallel lines, still flexible and damp. They shine slightly at the surface because the dough has just been compressed through metal. For penne, the die forms tubes. The dough flows around small internal pins that create the hollow center. As the tubes emerge, rotating blades cut them at an angle. Each cut creates the slanted ends that make penne recognizable. The pieces fall away in short lengths, still soft enough to bend, but firm enough to hold their hollow shape. For macaroni, curved tubes are shaped by dies that force the dough through bent channels or guide it into a curved path as it exits. For rigatoni, the die forms wide tubes, and ridges may be created by the die surface or shaping elements. For fusilli, the dough twists as it exits or is shaped by rotating guides that create a spiral. This is the hook inside pasta production. The same dough can become dozens of different products simply by changing the metal path it is forced through. The surface texture also depends on the die. Smooth dies create pasta with a cleaner, more polished surface. Bronze dies create a rougher texture because the dough drags against the metal more heavily. That rough surface catches sauce better, but it also requires careful drying because the texture holds moisture differently. Freshly extruded pasta contains too much moisture to be packed as dry pasta. It must be dried without cracking, bending, sticking, or collapsing. This drying stage is slower and more delicate than the extrusion itself. Long pasta follows one route. Spaghetti strands are lifted onto rods or spread across support systems so they hang straight. The strands must not touch too heavily, or they can stick together before their surfaces dry. The line keeps them separated while they enter the first drying zone. Short pasta follows another route. Penne, fusilli, shells, elbows, and rigatoni fall onto vibrating conveyors or perforated belts. The movement spreads the pieces into a shallow layer. Air can move around them from above and below. Pieces that clump together are separated before drying becomes permanent. The first drying stage is called pre-drying. Warm air removes surface moisture quickly. The outside of the pasta firms, just enough to prevent sticking, but the inside is still moist. If the surface dried too hard, too fast, moisture trapped inside would create cracks later. The process has to dry the outside without sealing the inside. The pasta then enters longer drying chambers. Temperature and humidity are controlled in stages. Warm air flows across the product, carrying moisture away. The pasta slowly loses water from the center outward. The goal is to bring moisture down to a stable level while preserving shape, color, and strength. Inside the pasta, starch granules and gluten, proteins form a rigid network as water leaves. The structure becomes hard and glassy. A soft, damp tube becomes a dry piece that can survive packing, shipping, and later boiling. The transformation is not just moisture loss. It is the creation of a stable internal architecture. Drying too quickly creates stress. The outside contracts before the center can shrink, and the pasta may crack. Drying too slowly wastes time and can weaken texture. The drying tunnel uses different zones so the pasta can adjust gradually. Heat, humidity, airflow, and residence time all work together. Long pasta must stay straight during drying. Hanging strands pass through zones where air moves evenly around them. If one side dries faster than the other, the strand can curve. The line controls airflow so each strand remains aligned. Short pasta must keep its shape. Hollow tubes cannot collapse. Spirals cannot unwind. Shells cannot flatten. The early drying step locks the shape, and the later drying steps strengthen it. Vibrating belts and perforated trays prevent pieces from piling too deeply. After drying, pasta enters a cooling zone. The hot, dry pasta cannot go directly into packaging. If packed while warm, trapped heat could create condensation inside the package. Cooling air brings the pasta closer to room temperature while keeping it dry. Now the line listens for defects. The cooled pasta moves through screens and sorting equipment. Broken pieces, fines, and dust fall away. For short pasta, vibrating screens separate undersized fragments. For long pasta, cutting systems trim strands to the correct length, and broken strands are removed before packing. Optical sorters can inspect color and shape. Pale spots, dark specks, burnt fragments, cracks, or misshapen pieces are detected as the pasta passes under cameras. Air jets remove defective pieces from the flow. The accepted pasta continues forward as a clean, uniform stream. For spaghetti and other long pasta, the strands are gathered into measured portions. The product aligns lengthwise. Mechanical guides square the ends and form bundles. The strands must be straight enough to slide into cartons or bags without snapping. For short pasta, the pieces enter weighing hoppers. The pasta flows like dry ceramic shapes, rattling across stainless steel surfaces. A multi-head or linear weigher measures each portion. The machine releases the correct weight into the packaging system below. Packaging depends on the format. For bagged short pasta, printed film unwinds from a roll. The film passes over a forming collar and wraps into a tube. A vertical seal closes the back. Horizontal jaws create the bottom seal. The weighed pasta drops into the open package. The jaws close again above it, sealing the top and cutting the bag free. The bag must protect the pasta from moisture. Dry pasta is stable only because its moisture level is low. The package keeps outside humidity from softening the product before it is cooked. For boxed pasta, flat paperboard blanks feed into a cartoner. Suction cups open the blank into a rectangular carton. Pasta is weighed or measured and dropped into the open box. Flaps fold in sequence. Glue or locking tabs secure the closure. The carton exits squared, filled, and ready for coating. Long pasta often enters cartons through a horizontal loading system. Bundles of spaghetti slide into opened boxes. The bundle must enter cleanly without bending. Folding rails close the flaps around the pasta. Adhesive secures the box while compression belts keep the shape square. Some pasta is packed in clear window boxes. The board carton includes a transparent film window. The pasta must align behind the window without dust or broken pieces clouding the view. The cartoner closes the box while keeping the window flat and clean. Every package passes through check weighing. Underfilled packs are rejected. Overfilled packs are also removed because they can strain seals or deform cartons. Vision systems check closure, print alignment, label position, and package shape. Metal detectors scan the sealed pack. Coding equipment prints production information onto the bag, box, or case. inkjet or laser marks appear while the package moves at line speed. Scanners confirm that the code is present and readable. Croissants reveal their layered structure when a cold butter sheet is locked inside dough and sent through the first laminating rollers. The dough surrounds the butter like an envelope. Its edges are sealed, but the inside is still separate. Dough outside, butter inside. The block moves toward paired rollers that lower with controlled pressure. As the rollers pull it forward, the butter spreads into a thin, continuous layer between sheets of dough. The block stretches longer, flatter, and wider without tearing. This first pass is the beginning of lamination. The croissant does not get its flaky texture from mixing butter into the dough. It gets it from keeping butter and dough in separate layers. Later, when heat enters the oven, water in the butter and dough turns to steam. That steam pushes the layers apart. But before that dramatic lift can happen, the factory has to build the layers with cold precision. The dough begins in an industrial mixer. Flour enters first after sifting. Sugar, salt, yeast, and milk powder or dairy ingredients are dosed in measured amounts. Water is added through temperature-controlled lines. Fat, or a small amount of butter, may enter the dough itself, but the main butter for lamination remains separate. The mixer works the ingredients only to the needed development. Croissant dough needs strength, but it cannot be overworked into a tight mass. It must stretch around butter, pass through rollers, and expand during proofing. The dough becomes smooth, cool, and elastic, with enough structure to hold gas and enough flexibility to fold. After mixing, the dough is divided into large slabs. These slabs pass into a cooling or resting stage. Resting relaxes the gluten so the dough can roll without shrinking back. Cooling firms the dough so it can match the butter texture. If the dough is warm and the butter is cold, the butter breaks into pieces. If the butter is soft and the dough is firm, the butter smears into the dough. Both must meet at nearly the same firmness. The butter is prepared as flat sheets. Blocks of butter or laminating fat pass through a butter sheet former. Rollers compress them into rectangles of even thickness. The sheet must be plastic, not brittle. It has to bend under pressure and spread evenly inside the dough. This hidden sheet is what will later become hundreds of delicate layers. The cool dough slab moves to the lock-in station. A butter sheet is placed on top. The dough folds over the butter from the sides or wraps around it completely. Edges meet and seal, trapping the butter inside. The block now contains alternating material, but only a few layers. The rollers will multiply them. The laminated block enters a sheeter. Rollers reduce its thickness gradually. The dough stretches and the butter stretches with it. The machine does not crush the block in one heavy pass. It reduces thickness step by step, so the butter remains continuous and does not burst through the dough. After the sheet reaches the target length, it folds. A folding device brings one end over the center and the other end over that, or folds the sheet in a book-style pattern. Each fold multiplies the layers. Dough, butter, dough becomes a stack. The stack is turned and sent through the rollers again. This is where the croissant's future texture is quietly being built. Every fold creates more layers. Every roller pass stretches them thinner. The sheet still looks like one pale slab from the outside, but inside it contains repeating bands of dough and butter. The dough rests between folds. Resting keeps the layers from tightening and tearing. The sheet is chilled again, so the butter stays firm. Temperature control is constant. Too much warmth makes the butter melt into the dough, destroying the clean separation. Too much cold makes the sheet crack at the folds. A second rolling pass lengthens the folded slab. The rollers pull it forward with steady pressure. The butter layers become thinner and more numerous. Another fold multiplies the structure again. The sequence may repeat, depending on the desired layer count and product style. When lamination is complete, the dough enters final sheeting. This pass brings the laminated dough to the exact thickness needed for cutting. The sheet moves as a long, wide ribbon. It must be even from edge to edge. Thin spots bake too crisp. Thick spots remain heavy. The rollers and side guides maintain a precise width and thickness. Now the shape appears. Cutting wheels slice the laminated sheet into long triangles. The blades move through the layers cleanly. A straight cut gives each piece sharp edges. The triangle shape is essential because it rolls into the curved croissant form. The wide base becomes the center body. The pointed tip wraps around the outside. The triangles may pass under a stretching device. This gently lengthens each piece, so the final croissant has more turns. The stretch must be controlled. Too much pull tears the layers. Too little gives a short, dense roll. Each triangle enters the rolling unit base first. Small belts or mechanical fingers catch the wide edge and roll it toward the point. The dough curls into a spiral. Layer after layer wraps around itself. The pointed tip lands on the outside and must sit underneath or near the base so the croissant does not unroll during proofing and baking. The rolled pieces may be curved slightly. Guide arms bend the ends inward to create the crescent shape. Straight croissants skip this curve and move forward as rolled cylinders with tapered ends. Both shapes depend on the same laminated triangle. The formed croissants are placed onto trays or oven belts with space between them. They are still dense and cool. The yeast has not fully expanded the dough yet. The next stage gives them volume, but it must happen gently. The croissants enter a proofing chamber. Warm, humid air surrounds them. Yeast produces carbon dioxide inside the dough layers. The pieces rise slowly. The spirals loosen slightly. The body becomes taller and softer. Humidity keeps the surface from drying and cracking. Proofing is delicate because the butter layers are still trapped inside. The chamber must be warm enough for yeast activity, but not so warm that the butter melts out before baking. If butter leaks early, the croissant loses lift and becomes greasy. The proofing conditions hold the dough at the edge of expansion without destroying lamination. The proofed croissants leave the chamber larger, softer, and more fragile. Their layers are visible around the edges. The surface may receive an egg wash or glaze before baking. A spray or rotating brush applies a thin coating across the top. This coating helps create a glossy, golden crust in the oven. Now the oven performs the loudest transformation. The croissants enter a tunnel oven or rack oven. Heat strikes the surface first. The butter layers begin melting. Water inside the dough and butter turns to steam. The steam expands between the layers, lifting them apart. The rolled structure inflates from within. Starbucks coffee begins revealing its character the moment green coffee beans tumble into a roaring drum roaster, because everything that follows depends on how those pale, dense seeds respond to heat over the next several minutes. The beans enter the roasting drum in a steady cascade, sounding more like small stones than something destined to become coffee. At first, they are cool, hard, and slightly green with very little aroma. As the drum rotates, every bean rolls continuously through streams of carefully controlled hot air, while the metal shell keeps them moving in constant circulation. The temperature climbs steadily, and moisture locked deep inside each bean begins escaping as steam. The color shifts almost unnoticed from pale green to yellow, then to light tan. This is only the beginning. The real transformation is still hidden inside the beans, and over the next several minutes, they will expand, crack, darken, and generate hundreds of aromatic compounds that did not exist when they first entered the machine. As heating continues, pressure builds inside every bean. Water trapped within the cellular structure converts to steam, while natural sugars and amino acids begin reacting with one another. through complex browning reactions. The beans swell noticeably as internal gases expand. Suddenly, a wave of sharp popping sounds echoes through the roasting drum. This first crack signals that internal pressure has fractured the bean structure, allowing moisture and gases to escape. The beans become lighter, more brittle, and significantly larger than when they entered. Although they now resemble roasted coffee, the roasting process is far from complete. Every additional second inside the drum continues reshaping flavor, aroma, color, and texture. The roast master, or automated roasting system, continuously monitors bean temperature, airflow, drum speed, and roast development. Hot air flows evenly through the rotating mass, ensuring every bean experiences similar conditions. Too little development leaves grassy or underdeveloped flavors. Too much heat risks burning delicate compounds before the desired profile is reached. Every adjustment happens gradually because thousands of beans must roast together with remarkable consistency. The changing aroma inside the roasting chamber becomes richer with every rotation as sugars caramelize, organic acids transform, and volatile aromatic compounds multiply throughout the batch. When the target roast profile is achieved, the entire batch empties rapidly into a cooling tray. Large paddles immediately begin sweeping through the beans, while powerful fans pull cool air upward from beneath a perforated floor. Cooling must happen quickly. Even after leaving the roasting drum, the beans still contain enough heat to continue roasting internally. Rapid cooling locks the roast level in place and prevents unwanted overdevelopment. The constant movement also keeps every bean exposed evenly to the cooling airflow, stopping the roasting process within minutes. Only after cooling does another important stage begin. Freshly roasted coffee contains large amounts of carbon dioxide generated during roasting. Rather than packaging immediately, the beans often enter holding bins where they rest for controlled degassing. During this period, carbon dioxide slowly escapes from inside the bean structure. Too much trapped gas could interfere with grinding, extraction, or package stability later. The beans continue releasing gas while preserving the aromatic compounds created during roasting, quietly preparing for the next transformation. Before any grinding takes place, the roasted beans move through extensive inspection systems. Vibrating conveyors spread them into thin layers, while optical cameras scan color, size, and overall appearance. Air separators remove lightweight fragments and loose chaff produced during roasting. Magnets capture any stray metallic particles before the beans continue forward. Every stage protects the consistency of the finished coffee while ensuring only properly roasted beans. Advance to processing. Some Starbucks products are packaged as whole beans, but ground coffee follows another path entirely. The roasted beans travel toward industrial grinders equipped with precision-engineered rollers. Unlike household grinders, these machines reduce the beans gradually through multiple stages. The first rollers crack the beans into coarse pieces. Additional rollers continue reducing particle size until the grind matches the intended brewing method. Every adjustment changes extraction behavior later. A finer grind exposes more surface area to water, while a coarser grind slows extraction. Particle size distribution is monitored continuously because even small variations can alter the finished beverage. The freshly ground coffee moves through enclosed transfer systems designed to minimize unnecessary exposure to oxygen. Grinding dramatically increases surface area, making the coffee more vulnerable to aroma loss if left exposed. Conveyors, sealed hoppers, and enclosed augers transport the grounds efficiently while preserving as much freshness as possible. Depending on the final product, the grounds may proceed directly toward packaging or continue into extraction for ready-to-drink beverages. For bottled Starbucks coffee drinks, extraction begins inside large stainless steel brewing vessels. Precisely weighed coffee grounds enter brewing chambers where carefully controlled water begins flowing through the coffee bed. Temperature, contact time, pressure, and flow rate all influence how soluble compounds dissolve into the brewing water. As hot water travels through the grounds, it extracts oils, sugars, acids, aromatic compounds, and dissolved solids that create the recognizable coffee flavor. The liquid leaving the brewer is no longer water. It has become concentrated brewed coffee. The brewing process is carefully balanced. If water passes too quickly, desirable compounds remain trapped inside the grounds, producing a weak extract. If extraction continues too long, harsher compounds begin dissolving, creating bitterness that overwhelms the finished beverage. Automated controls continuously monitor flow rates and brewing parameters to maintain consistency from batch to batch. After extraction, the brewed coffee separates from the spent grounds through filtration systems. Fine screens and filters remove remaining particles while allowing the coffee extract to continue flowing into insulated holding tanks. The used grounds leave the brewing equipment through separate discharge systems, while the clarified coffee continues deeper into production. Now another transformation begins. Depending on the product, ingredients such as milk, cream, sugar, or flavor components are prepared separately before blending. Milk enters refrigerated storage tanks and may undergo additional standardization to achieve the desired fat content. Sweeteners dissolve into controlled syrup systems. Flavor ingredients are measured through precision dosing equipment. Each component waits independently until blending begins. Inside large blending tanks, brewed coffee combines with these prepared ingredients according to the intended formulation. Agitators circulate the mixture continuously, ensuring every portion becomes completely uniform. The dark coffee gradually changes as lighter dairy ingredients disperse throughout the liquid, creating smooth, consistent color and body. Every addition is monitored by automated flow meters and weighing systems to maintain exact proportions throughout the batch. Before packaging, many ready-to-drink coffee products undergo pasteurization or ultra-high temperature processing. Plate or tubular heat exchangers rapidly raise the beverage to carefully controlled temperatures before cooling it again just as quickly. This thermal treatment improves product stability while preserving as much of the coffee character as possible. Temperature sensors monitor the beverage continuously, ensuring every portion receives the required treatment before moving forward. The finished coffee beverage enters insulated holding tanks equipped with slow-speed agitators. Gentle circulation prevents separation while minimizing unnecessary air incorporation. Level sensors monitor available volume, automatically supplying the filling lines as production continues. Meanwhile, empty bottles begin their own journey. Plastic bottles often start as PET preforms, compact plastic tubes already containing the finished neck and threaded opening. Infrared heaters soften the body section while keeping the neck cool. Stretch blow molding machines then pull and inflate each preform inside precision molds, forming the familiar bottle shape within seconds. Every bottle exits lightweight, yet strong enough to withstand filling and transportation. Glass bottles arrive already formed and move through inspection systems before entering internal rinses. Powerful, filtered air or sterile water removes any loose particles. Every container proceeds toward the filling line clean and ready. Lipton iced tea takes its first recognizable form when a stream of freshly brewed tea flows out of enormous extraction vessels, carrying thousands of dissolved flavor compounds that only minutes earlier were locked inside dry tea leaves. At that moment, the liquid already has its deep amber color and unmistakable aroma, but it is still only one part of a much larger process. Before this tea can become the finished drink found on store shelves, it must be blended, refined, cooled, packaged, and protected with remarkable precision. The brewing stage may look like the climax, yet it is only the opening chapter. The next transformations happen almost invisibly inside a network of stainless steel tanks, insulated pipelines, and high-speed filling equipment, where every second and every degree of temperature influences the final beverage. The tea leaves begin their journey long before brewing ever starts. Large deliveries arrive at the processing facility and are transferred into enclosed storage systems designed to keep moisture and contaminants away from the raw ingredient. Before the leaves enter production, automated sampling systems verify their physical characteristics, while vibrating screens remove dust, stems, and oversized particles. Magnets capture any stray metallic fragments that could have entered during transportation. The cleaned leaves move through enclosed conveyors toward precisely controlled weighing stations. Every batch must begin with the exact amount of tea, because even small variations influence extraction strength later in the process. Once the required quantity is measured, the leaves travel toward the brewing room, where massive extraction vessels are already being prepared. Meanwhile, treated water begins its own entirely separate journey through the factory. Since water makes up the overwhelming majority of the finished drink, consistency starts here. Incoming water passes through multiple stages of purification, including coarse filtration, activated carbon treatment, and fine polishing systems that remove unwanted tastes, odors, and microscopic particles. Depending on the facility, mineral content may also be carefully adjusted to create a stable brewing base. The treated water collects inside insulated storage tanks until production calls for the next batch. Powerful pumps then send it through plate heat exchangers, where its temperature rises rapidly before entering the extraction vessels. At this point, two completely separate ingredients, carefully prepared water and measured tea leaves, are finally ready to meet. Inside the extraction tanks, hot water begins flowing evenly through the tea leaves. Agitation systems circulate the liquid gently, allowing water to contact every portion of the leaves without damaging them excessively. Heat unlocks thousands of naturally occurring compounds, including color pigments, aromatic molecules, tannins, and soluble flavor components. Gradually, the clear water darkens into a rich amber infusion as extraction continues. Sensors continuously monitor brewing temperature, contact time, and circulation speed, because every adjustment changes the final flavor profile. If brewing stops too early, valuable compounds remain trapped inside the leaves. If it continues too long, stronger tannins begin dominating the extract. The process must stop at precisely the right moment to capture the desired balance before the tea changes character. Once brewing reaches its target, the liquid begins separating from the leaves. Stainless steel screens hold back the spent tea, while the freshly brewed extract flows into enclosed transfer lines. Additional filtration removes smaller leaf particles, creating a smooth liquid while preserving the dissolved flavor compounds developed during extraction. The tea now carries its recognizable aroma and color, but it remains far stronger than the finished beverage. This concentrated extract serves as the foundation for everything that follows. Hidden behind the walls of the blending room, the next stage quietly determines how every bottle will taste. Large blending tanks wait nearby, already connected to treated water lines, sweetener systems, and ingredient dosing equipment. Before the brewed tea enters, sweetener preparation has already begun. If granulated sugar is used, automated feeders deliver carefully measured quantities into heated mixing tanks where powerful agitators dissolve every crystal into a perfectly clear syrup. In facilities using liquid sweeteners, insulated pipelines transfer the ingredient directly into the blending system, while electronic flow meters monitor every addition. Regardless of the sweetener source, the objective remains identical: produce a completely uniform liquid capable of blending instantly with the tea extract. The syrup is filtered before leaving the preparation area, ensuring no undissolved particles continue downstream. Now the brewing room and syrup room finally connect. Concentrated tea flows into the blending vessel while sweetener enters through separate dosing lines. Treated water follows immediately afterward, reducing the concentrated tea to its intended drinking strength. Agitators circulate the growing batch continuously, eliminating concentration differences throughout the tank. Depending on the specific Lipton iced tea variety, fruit juice concentrates, natural flavors, citrus components, or additional ingredients may enter through precision metering systems. Every ingredient joins the circulating liquid gradually, disappearing almost immediately into the constantly moving mixture. From above, the blending tank appears calm, but beneath the surface, every rotation of the agitator creates complete uniformity. The beverage now resembles the finished product remarkably closely, yet another critical transformation still lies ahead before packaging can even begin. Before filling, the tea beverage usually undergoes thermal processing designed to stabilize the product while preserving as much flavor as possible. The liquid travels through enclosed stainless steel plate heat exchangers, where thin metal plates separate the beverage from heating and cooling media. Heat transfers rapidly across the plates, raising the beverage to carefully controlled temperatures for only the required amount of time. Immediately afterward, another section of the exchanger cools the beverage again. The rapid heating and cooling sequence protects product quality while preparing the beverage for packaging. Sensors monitor temperature continuously, and automated valves divert product instantly if processing conditions fall outside specification. Although this stage occupies only a short section of the production line, it plays an essential role in preparing the beverage for its journey beyond the factory. After thermal treatment, the tea flows into insulated holding tanks equipped with slow-moving agitators. Unlike the vigorous mixing performed earlier, these paddles rotate gently, keeping ingredients evenly distributed without introducing unnecessary air. Dissolved oxygen can gradually influence flavor stability, so every transfer throughout the factory is designed to minimize turbulence wherever possible. Level sensors monitor every storage tank, while automated control systems continuously balance supply between production batches and multiple filling lines operating simultaneously. The beverage now waits only briefly before the fastest machines in the factory take over. At the opposite end of the production hall, empty containers begin their own, carefully synchronized journey. Plastic bottles commonly start as PET preforms, compact plastic tubes already containing the finished threaded neck, but lacking the familiar bottle shape. The preforms enter infrared heating ovens where they rotate continuously beneath carefully arranged heating elements. Only the body softens while the neck remains cool and dimensionally stable. Once heated, each preform enters a stretch blow molding machine where a stretch rod pulls downward through its center as high-pressure compressed air expands the softened plastic outward against chilled mold walls. Within seconds, every contour appears: the shoulder, base, sidewalls, grip panels, and label surface. The bottle exits lightweight yet remarkably strong, immediately joining high-speed air conveyors that transport it toward the filling room. Before filling begins, every bottle passes through an internal cleaning station. Bottles invert, while filtered air removes any particles that may have entered during handling. They rotate upright again and move directly toward the rotary filler. At the same time, chilled Lipton iced tea leaves the holding tanks through sanitary stainless steel pipelines and approaches the filling bowl from an entirely separate direction. Two production streams that have remained independent until now finally meet. The rotary filling machine operates with remarkable synchronization. Empty bottles enter continuously through star wheels that position each container beneath an individual filling valve. As the carousel rotates, Valves open precisely when each bottle reaches the correct position. The amber-colored tea flows smoothly into the waiting container, while electronic controls monitor the fill level continuously. Every bottle receives nearly identical volume despite the tremendous production speed. Once the programmed level is reached, the valve closes instantly before the next bottle arrives beneath it. The entire sequence repeats thousands of times every hour with barely noticeable variation. Filled bottles move immediately into the capping turret. Plastic closures arrive from vibrating sorting bowls that orient every cap correctly before feeding spinning capping heads. Each head applies carefully controlled torque, tightening the cap enough to create a secure seal while avoiding thread damage. Within only a few seconds of leaving the filler, every bottle is completely closed and protected from the outside environment. Now another important checkpoint begins. Vision inspection systems examine every bottle without slowing production. Cameras verify fill height, cap position, bottle shape, closure integrity, tamper bands, and overall appearance. Check weighers confirm product quantity, while automated reject mechanisms remove any bottle that falls outside specification. Every accepted bottle continues toward labeling, where another series of precisely synchronized machines prepares the product for retail shelves. Printed label film unwinds continuously from large reels, while electronic registration sensors monitor alignment marks. Rotary knives cut individual labels before adhesive secures the leading edge against each bottle. As the bottle spins, the remaining label wraps smoothly around the surface before pressure rollers eliminate wrinkles and air pockets. Some packaging formats instead receive shrink sleeves that slide over the bottle before passing through heated tunnels, where the printed film contracts tightly around every contour. Coding systems immediately apply production information, including batch identification and manufacturing details, before cameras verify that every printed code remains readable. The production line now begins, transforming individual bottles into retail-ready multi-packs. Guide rails divide the continuous bottle flow into multiple lanes, while timing screws establish exact spacing. Automated grouping systems assemble bottles into 6-packs, 8-packs, or larger retail configurations depending on production requirements. Shrink film wraps around grouped bottles before entering heated tunnels, where controlled heat causes the film to contract tightly around every container, creating compact and stable bundles. Other product formats enter paperboard cartoning systems, where flat carton blanks open automatically before bottles slide neatly inside. Folding mechanisms close the cartons, while hot melt adhesive secures every seam. Tim Hortons donuts reveal their unmistakable shape the instant a soft ring of dough drops onto a moving conveyor. But that perfect circle is only the beginning of a much longer transformation. At first glance, it looks complete, already resembling the finished donut. Yet, it is still nothing more than cool, unbaked dough with no crust, no airy interior, and none of the glossy coatings that will eventually define the finished product. As the conveyor carries each freshly formed piece deeper into the bakery, every stage ahead builds upon the last. The next few minutes will stretch the dough, fill it with thousands of microscopic air pockets, bake it into a delicate structure, and finally coat it in layers of glaze, icing, or toppings. Every machine waits for the previous one to finish its work, creating a seamless chain of transformations where even a slight change in timing affects everything that follows. Long before the first donut reaches the forming line, ingredients have already begun their own carefully coordinated journey. Flour arrives in bulk and moves pneumatically into towering storage silos where it remains dry and protected until production begins. Metering systems deliver precise quantities into industrial mixers, while separate ingredient feeders prepare sugar, salt, yeast, milk solids, shortening, emulsifiers, and carefully measured water. Every ingredient enters according to a programmed sequence because dough development depends not only on the recipe, but also on the order in which each component is introduced. Powerful spiral mixing arms rotate through the bowl, while the dough gradually transforms from loose dry particles into one continuous elastic mass. At first, it appears rough and uneven, but with every revolution, the gluten network strengthens, allowing the dough to stretch while trapping the gases that will later create its light interior. Once mixing reaches the desired level of development, the dough leaves the mixer in large portions and travels toward resting equipment. Although nothing dramatic appears to happen during this stage, the dough is quietly preparing itself for the mechanical work ahead. Resting allows the gluten structure to relax after intensive mixing, making the dough easier to shape without excessive shrinking or tearing. Temperature remains tightly controlled because warmer dough behaves very differently from cooler dough. Sensors continuously monitor both dough temperature and resting duration before conveyors automatically release each batch toward the forming line. The dough now has the strength to hold its shape while remaining soft enough for precise forming. The forming equipment begins by feeding the rested dough through sets of sheeting rollers. Each roller gradually reduces thickness without crushing the internal structure. The dough becomes a smooth, continuous sheet moving steadily across wide conveyor belts. Thickness must remain remarkably uniform because even slight variations would produce donuts that bake differently. Optical sensors monitor the sheet while automated adjustments compensate for any inconsistencies before the dough reaches the cutting station. Now comes one of the fastest transformations in the entire bakery. Rotary cutters descend rhythmically onto the moving sheet, stamping out perfectly shaped donut rings with astonishing speed. Circular cutters remove both the outer edge and the center hole simultaneously, producing hundreds of identical pieces every minute. The remaining scrap dough surrounding the cut shapes does not go to waste. Conveyors carry it away to be blended carefully with fresh dough in controlled proportions before entering production again. The newly cut rings continue forward untouched, maintaining smooth edges that will later expand evenly during baking. At this point, the donuts still appear dense and flat. Their greatest transformation has yet to happen. Conveyors transport the freshly cut rings into a large proofing chamber where carefully controlled warmth and humidity awaken the yeast. Inside this enclosed environment, countless tiny bubbles of carbon dioxide begin expanding throughout the dough. The rings slowly increase in height while becoming noticeably softer and lighter. The surface remains smooth because humid air prevents premature drying. Every minute inside the proofer builds the internal structure that will later support the finished donut. Too little proofing leaves the crumb compact, while too much causes the delicate structure to weaken. Timing therefore becomes just as important as every ingredient measured at the beginning of production. As the proofed donuts leave the chamber, they hardly resemble the dense rings that entered only a short time earlier. Their volume has increased dramatically, and their surfaces now feel delicate enough that every conveyor transition must support them gently. Yet, despite their impressive rise, another transformation still lies ahead, one that permanently fixes their structure and creates the familiar golden crust. Instead of entering a fryer, many large-scale Tim Hortons production facilities prepare donuts through controlled baking systems before finishing. The proofed rings travel into long tunnel ovens, where multiple heating zones surround the dough with carefully regulated temperatures. Heat first begins setting the outer surface while the interior continues expanding. Water trapped inside the dough converts to steam, stretching the already enlarged air cells created during proofing. Proteins strengthen into a permanent network while starches gelatinize, giving the donut its soft but resilient crumb. As the conveyor advances through each heating zone, the pale dough gradually changes color, developing a light golden exterior while maintaining a moist interior. The exit from the oven introduces another critical stage that receives far less attention than mixing or baking, but is equally important. Freshly baked donuts contain considerable internal heat. If they moved immediately into icing or glazing, excess warmth would thin the coatings and prevent proper adhesion. Cooling conveyors therefore stretch across long sections of the bakery, allowing air to circulate gently around every donut. During this journey, the crumb stabilizes, the crust firms slightly, and excess moisture redistributes throughout the interior. By the time the donuts reach the finishing area, they have cooled enough to receive decorative coatings without compromising texture. Now the bakery begins creating the enormous variety associated with Tim Hortons donuts. Plain donuts branch toward packaging almost immediately, but many others enter glazing systems, where warm glaze continuously circulates through shallow reservoirs. As each donut passes beneath the glazing curtain, its upper surface becomes coated with a thin, glossy layer. Excess glaze drains away, while the remaining coating gradually sets into a smooth, slightly translucent finish. The process lasts only seconds, yet it completely changes the appearance of the product. A high-volume Dunkin' Donuts line is built around delivering dough or batter to hot oil in the same condition every minute, because frying fixes shape, crumb, and surface in seconds and leaves little opportunity to correct variation downstream. Ingredient conditioning starts the process. Flour is sieved to remove lumps and aerated for consistent hydration. Sugar is screened so crystal size stays stable and dissolves predictably in mixes. Salt and leavening are pre-blended, so distribution is uniform at low inclusion rates. Fats are tempered so their plasticity is consistent for dough systems, or melted and cooled to a target temperature for batter systems. Eggs and dairy liquids are tempered because small temperature shifts change emulsion behavior and batter viscosity. Water temperature is selected to land the final dough or batter in a narrow temperature window. For yeast-raised donuts, the front end is a developed dough that must proof consistently. Flour enters a mixer and is hydrated with water and dairy liquids, while yeast is dispersed early, so fermentation is uniform. Mixing begins slowly to hydrate without dusting, then increases speed to develop gluten. Gluten development is tuned to a target elasticity that can trap gas but still sheet cleanly. Fat is added after initial gluten formation, so it softens the network without blocking development. Eggs and emulsifiers are incorporated in a controlled sequence, so they form a stable dispersion inside the dough rather than separating into streaks. Dough temperature is managed as a primary control variable. Mixing friction generates heat, so water temperature and mix time are adjusted to reach a target dough exit temperature. That exit temperature controls dough stiffness and yeast activity. The dough then enters a timed rest, where moisture equalizes and gluten relaxes. Relaxation reduces snapback in sheeting and improves cut accuracy, while early fermentation begins creating fine gas cells without fully expanding the dough. The rested dough feeds a divider and sheeter. Dividing stabilizes feed rate into rollers, so thickness remains steady across time. Sheeting reduces thickness through several roller gaps rather than one large reduction to avoid stress lines that later become weak points in the fryer. Gauge rollers lock the final sheet thickness, which becomes a main determinant of donut weight and final crumb thickness. Rotary cutters punch rings at line speed, cutting an outer diameter and removing the center plug. Cutter sharpness matters because dull edges compress the dough and create ragged rims that absorb more oil and brown unevenly. Scrap around the cutouts is lifted and returned to the dough stream at controlled ratios, because high scrap ratios increase working and shift gluten development. Cut rings move into proofing, where the dough expands to near final volume. Proofing is run at controlled temperature and humidity. Temperature sets yeast gas production rate, and humidity prevents a dry skin that would restrict expansion and cause blowouts. Proof time is tuned to reach a target volume and cell structure. Underproof yields dense donuts with limited lift. Overproof yields fragile donuts that collapse when moved or flipped in oil. For cake-style donuts, the line works with a chemically leavened batter rather than a fermented dough, so the objective is minimal gluten with uniform leavening dispersion. Dry ingredients are pre-blended, so chemical leavening and salt are evenly distributed. Liquid ingredients are blended separately, so eggs and fats emulsify before meeting flour. The streams combine and mix only long enough to hydrate flour and remove lumps, because overmixing develops gluten and produces tough donuts with irregular cracking. Batter temperature is held tightly because viscosity must remain stable for depositing. If batter is too thin, it spreads and loses ring definition when it hits oil. If too thick, it deposits unevenly and can trap air pockets that create voids. Depositing forms rings directly into the fryer for cake products. A depositor meters batter through shaped nozzles with timing synchronized to the fryer conveyor, so spacing is consistent. Deposit weight is controlled by pump stroke or timed flow. The batter must release cleanly from the nozzle and hold its shape long enough for the surface to set in oil. Frying is the setting step for both routes. Oil temperature, dwell time, and turnover are the controlling variables. When a donut enters oil, surface water flashes to steam, creating outward pressure that expands the structure and delays oil penetration during the earliest phase. Starch gelatinizes at the surface and forms a crust. Proteins coagulate and lock the structure. Browning reactions accelerate as the surface dries, creating the final color and flavor profile of the crust. Yeast-raised rings usually float and fry on one side first. Conveyor speed determines how long the first side sets before a turning mechanism flips the donut. Flip timing is critical. Flipping too early deforms the ring and creates flat spots. Flipping too late creates an overly thick crust on one side and uneven color. The second side fry completes structure set and balances moisture loss, so the donut does not warp. Cake donuts set more quickly because the batter begins as a suspension with chemical gas release and rapid heat penetration. Fry conditions are tuned so the surface sets at the right moment. If the surface sets too fast, expanding gases crack the crust and create blowouts. If the surface sets too slowly, the batter spreads and forms misshapes. Residence time and temperature are adjusted together to manage this balance. Oil management runs continuously because crumb fragments and batter fines burn and darken the oil, changing heat, transfer, and color development. Filtration removes fines and keeps the oil clean. Oil is circulated to maintain uniform temperature across the fryer width and prevent striping. Controlled oil turnover keeps frying behavior stable, so the same dwell time produces the same color and oil pickup. As donuts exit the fryer, surface oil is removed immediately. Drain belts and vibrating conveyors shake off free oil, and air blowers strip oil from creases. This step is important because surface oil interferes with glaze adhesion and increases greasy feel. The donuts then enter cooling, where internal steam condenses, fats begin to crystallize, and the crumb firms. Cooling is staged to stabilize structure and prepare for finishing. Hot donuts are soft because fats are liquid and the crust is still plastic. As they cool, the crust becomes rigid and the interior moisture redistributes. Cooling airflow is controlled so the surface does not dry too fast, which would create a tough crust that flakes under glaze. Cooling also prevents packing too warm, because warm donuts release moisture into packages and soften coatings. Glazing and icing are applied in controlled viscosity windows. A classic sugar glaze is mixed to a defined solids level and held warm enough to flow as a thin film. Donuts pass under a glaze curtain or are dipped, and the excess drains as they travel on a setting conveyor. As water evaporates, the glaze crystallizes into a smooth shell. Chocolate or fat-based icings are heated to a target flow temperature and applied by curtain or dipping, then set by cooling so the fat network solidifies without cracking. Powdered sugar or cinnamon sugar finishes are applied while the donut surface still has slight warmth and tack. The donuts pass through a shower or drum that distributes powder evenly, and screens recover excess. Toppings are applied during the short tack window before coating set. Feeders meter sprinkles or nut pieces at a rate synchronized to belt speed, so coverage stays uniform without clumps. Filled donuts at an injection step after cooling reaches a firm but pliable state. Fillings are prepared to a pumpable viscosity that holds shape without leaking. Multi-needle injectors penetrate at controlled depth, and piston strokes deliver consistent doses. Needle retraction timing is coordinated to reduce backflow and surface smearing. If a side fill format is used, a controlled slit is cut, and a nozzle deposits filling into the pocket. Then the product passes through a brief set zone so the filling surface stabilizes. Packaging is designed around protecting finishes and managing moisture exchange. Donuts intended to stay soft use barrier materials that reduce moisture loss. Donuts with a crisp shell need packs that prevent moisture gain that would soften crust and glaze. Cartons and clamshells protect toppings from abrasion and reduce contact marks, while flow wrap provides strong moisture control but requires the surface to be fully set to avoid smearing. Seal temperature and dwell are tuned so seals close without heating the donut enough to soften coatings. A Chick-fil-A style breaded chicken fillet is produced by turning trimmed poultry breast into uniform portions, conditioning the meat so it stays juicy after cooking, applying a controlled flour and batter system that bonds tightly, setting the coating quickly in hot oil, then chilling and packaging so every fillet reheats with the same crust and bite. Production starts with raw poultry arriving chilled and moving into size reduction and standardization. Breast meat is trimmed to remove thin tails and ragged edges that would overcook and create hard spots. The trimmed pieces are sorted by weight band so the forming line can hold a tight portion range. Consistent portion mass is a core control because fry time and internal temperature rise rate depend on thickness. The meat is then conditioned to stabilize moisture, retention, and texture. A measured solution is prepared from water, salt, and functional ingredients that improve binding and reduce purge. This solution is mixed to a defined concentration and held cold so it does not warm the meat. The solution is introduced to the meat by tumbling or by injection followed by tumbling. Tumbling cycles alternate between rotation and rest so the solution distributes through muscle fibers without tearing them. Vacuum tumbling is often used because removing trapped air improves uptake consistency and reduces voids that can appear as soft pockets after cooking. The endpoint is judged by pickup percentage and by uniform surface tack rather than by extended mixing time. Once conditioned, the meat is portioned into fillet shapes. If whole muscle fillets are used, they are pressed to a consistent thickness using calibrated rollers. Pressing is gentle and aims to widen and even the piece without shredding. Thickness control matters because a thick center can remain undercooked when the crust looks done. If formed fillets are used, the meat is ground coarsely and then shaped in a forming machine. But a classic sandwich fillet format typically relies on whole muscle thickness control rather than full comminution. After shaping, the fillets pass through a brief chill stage. Chilling firms the surface proteins and improves handling so the pieces do not smear when they enter the coating system. Chilling also stabilizes the pickup behavior of the next layers because warmer surfaces thin the batter and increase coating variability. The coating system is built as a multi-step adhesion stack. The first layer is a pre-dust, usually a seasoned flour blend that absorbs surface moisture and creates a dry interface. Pre-dust is delivered as a curtain or bed where fillets tumble and roll so all surfaces are covered. Excess pre-dust is removed by gentle shaking because too much dry flour creates thick patches that later detach. After pre-dust, the fillets enter a batter stage. The batter is mixed in tanks that maintain solid suspension and viscosity. Viscosity is monitored because it determines coating thickness and how the batter bridges surface contours. Batter temperature is controlled because warm batter flows too thin and produces weak coating, while cold batter thickens and creates ridges. The fillets pass through a batter waterfall or immersion where every surface is wetted. Air knives can remove excess and set a uniform film thickness. Breading follows immediately while the batter is still wet. Breading is usually a seasoned flour system with a defined particle size distribution. Some formats use a mix of fine flour and larger crumb to create a textured crust. The fillets travel through a bed of breading while top belts press lightly to embed particles. This compression step is critical because it turns loose surface flour into a mechanically locked layer that will survive frying and later handling. Excess breading is removed so the crust is thick but not clumpy. If the target crust requires a distinctive, craggy surface, the line can use a second batter and breading pass. The first pass builds the base, and the second pass builds height and texture. Each pass is tuned, so the coating does not become so heavy that it insulates the meat and slows cooking. After breading, the fillets enter a short setting zone before frying. This can be a brief rest on a belt that allows the batter to hydrate the dry breading and form a cohesive paste at the interface. Hydration improves adhesion and reduces blow-off in the fryer. The rest time is short because the coating must not become wet enough to smear. Frying is the structure setting step. Fillets enter a continuous fryer where oil temperature and dwell time are tightly controlled. The fillets are held under oil by a top belt so they cook evenly and do not float and curl. As the fillet enters oil, surface water flashes to steam. That steam creates outward pressure that expands the coating slightly and forms pores. Starches in the batter gelatinize and then begin to dry into a rigid network. Proteins in the batter coagulate and lock the crust shape. Oil temperature is chosen to set the crust quickly while allowing heat to penetrate the meat at a controlled rate. If oil is too hot, the crust darkens before the center reaches the target internal temperature. If oil is too cool, the crust sets slowly, absorbs more oil, and becomes heavy. Dwell time is set by belt speed and fryer length. Bed loading is controlled because overcrowding reduces oil circulation and causes uneven color. Oil management runs continuously because breading fragments break off and will burn if not removed. Filtration systems remove fines and keep the oil clean. Circulation keeps temperature uniform across the fryer width. Fresh oil makeup maintains quality so heat transfer and browning stay consistent. At fryer exit, surface oil is removed by vibration and air stripping. Removing surface oil reduces greasiness and improves how the fillets package and reheat. The fillets then enter a cooling stage. Cooling stabilizes the crust and lets internal steam pressure fall gradually. If cooling is too fast, the crust can contract and separate slightly. If cooling is too slow, residual heat can soften the coating and reduce crispness. From here, the process can diverge depending on distribution format. For a chilled product, the fillets are cooled rapidly to a target core temperature and held under controlled conditions. For a frozen product, the fillets enter an individual quick freezer. The freezer uses high-velocity cold air to freeze quickly and preserve crust porosity. Rapid freezing forms smaller ice crystals and reduces moisture migration that would soften the crust later. The pieces are spaced so they freeze individually and do not stick. After freezing, the fillets are screened and inspected. Broken coating fragments are removed because they increase crumbs in the package and can burn during reheating. Size and weight checks confirm portion control. Optical systems can reject misshapes and incomplete coating. Metal detection can be placed after freezing when product flow is stable. Packaging begins with portioning. Multi-head weighers or counting systems assemble target weights for bags or cases. Drop heights are minimized because frozen breading can chip and create fines. Bags are formed from barrier film that limits moisture exchange. Moisture control is crucial because the crust will lose crisp potential if it picks up moisture in storage. Seals are made with controlled heat so the film closes without wrinkles. Seal areas must remain clean because crumbs can interfere with seal integrity. For food service formats, the fillets are packed into lined cases with internal bags. Case fill patterns are chosen to reduce compression on lower layers. Cases are sealed and coated. Pallet stacking is designed to avoid crushing that would fracture crust. Storage temperature stability prevents freeze-thaw cycles that create ice crystals on the crust and degrade reheating performance. The final product performance is engineered into the factory steps. Meat conditioning sets moisture retention, so the fillet stays juicy after a high heat finish. Pre-dust and batter create a bonded interface, so the crust does not slide off when bitten. Breading particle size and compression set the surface texture. Fry temperature sets pore structure and crust rigidity. Cooling and freezing preserve that structure. Packaging maintains low moisture exchange so the crust can crisp again during final cooking or reheating. A McDonald's-style hamburger is manufactured by turning beef trim into uniform patties that cook the same way every time, producing buns that stay soft yet resilient after freezing and toasting, then portioning and packaging each component so it can be assembled rapidly with consistent texture. Beef patty production starts with raw trim selection and temperature control because fat level and grind behavior determine bite and shrink. Beef arrives as chilled trim in defined lean to fat bands. The trim is inspected for hard connective pieces that would create tough spots and for excessive surface fat that would smear during grinding. Trim is kept cold from the start because warm fat smears into a paste, which causes dense patties and poor cook texture. The trim enters a coarse grinding stage first. Coarse grinding breaks the meat into uniform chunks without turning it into an emulsion. This is done through a grinder plate with larger holes, so particle definition is preserved. The coarse ground meat then moves to blending, where multiple trim lots are combined to hit a target fat percentage. Blending uses paddles that fold the meat rather than whip it, because air incorporation and overworking change density and can create voids. After blending, the meat is ground again through a finer plate to create the target particle size distribution. Particle size affects how the patty binds and how it releases juices. Too coarse yields a crumbly patty that breaks at the edges. Too fine yields a tight, rubbery bite. Grind temperature is monitored continuously because friction can warm the meat. If temperature rises, the line slows or adds colder meat to keep the mix in range. The blended grind is moved quickly to forming. Forming turns the loose ground meat into patties with a fixed diameter, thickness, and mass. A patty former meters meat into a cavity and compresses it to a set density. Compression must be strong enough to make the patty hold together during freezing and handling. Compression must not be so strong that the patty becomes dense and loses its characteristic bite. Formers often imprint a pattern on the surface. The imprint increases surface area and helps heat penetrate evenly during cooking. Weight control is enforced at the forming head. Portioning is measured by volume with density control or by mass flow with feedback. Tight weight control is important because cook time is fixed in high volume systems, so patties must reach target internal temperature within the same dwell. Patty thickness control is equally critical because a thicker patty heats slower and will be underdone when a thinner one is correct. Immediately after forming, patties enter a rapid freezing step. Freezing locks the shape and prevents patties from sticking together. Individual quick freezing is used with high-velocity cold air. The patties travel on a belt through a tunnel where cold air freezes the surface quickly first, then drives the core down to the target temperature. Rapid freezing forms smaller ice crystals and preserves texture better than slow freezing, which can create larger crystals that damage muscle structure. Patties are then separated, counted, and stacked into interleaved layers. Interleaving uses paper or film sheets between patties to prevent adhesion and simplify later separation. Stacking pressure is controlled so patties do not deform. The stacks are bagged or boxed in a way that limits moisture exchange and protects edges from chipping. Metal detection and weight verification typically occur after freezing when product flow is stable and consistent. The bun is produced on a separate bakery line built around controlling softness, resilience, and freeze-thaw stability. Flour is sieved and blended to a target protein range because gluten strength controls how the bun holds up to toasting and compression. Sugar and salt are metered precisely. Yeast is staged as a controlled addition because fermentation rate must match line speed. Fats and emulsifiers are included to soften crumb and extend softness after freezing. Water temperature is controlled because dough temperature drives fermentation speed and dough handling. Mixing develops gluten to a defined endpoint. The dough must be strong enough to trap gas and rise, but not so strong that the bun becomes chewy or tough. Mixing begins with hydration and then transitions into higher energy kneading until the dough reaches a smooth, elastic state. Dough temperature is checked at discharge because mixer friction can warm the dough and accelerate fermentation. If dough exits too warm, proof times shorten and the process becomes unstable. After mixing, dough is rested and then divided. Dividers. Portion dough into equal pieces by weight. Portion weight directly determines bun diameter and height. Divided pieces are rounded to create surface tension, which supports a uniform shape during proofing. Rounded dough balls then rest briefly to relax so they can be shaped without tearing. Shaping forms the final bun geometry. Dough balls are flattened slightly and placed onto baking trays or oven bands. Proofing follows in a warm, humid environment. Proof temperature controls yeast activity and gas generation. Humidity prevents skin formation so the bun can expand smoothly. Proof time is tuned so buns reach a target volume and internal cell structure. Underproof yields dense buns with low softness. Overproof yields weak buns that collapse and wrinkle. Baking sets structure and dries the bun to a controlled moisture endpoint. Tunnel ovens run zoned heat so the surface sets and the crumb cooks without excessive crust hardness. Early oven zones drive oven spring as trapped gas expands. Mid zones gelatinize starch and coagulate proteins to fix the crumb. Later zones develop a light crust color and finish internal moisture reduction. The bun must not be too dry because it will feel stale. It must not be too wet because it will collapse and compress poorly. After baking, buns cool on conveyors with controlled airflow. Cooling sets the crumb as fats crystallize and moisture redistributes. Slicing is done after cooling reaches the right firmness. Slicers cut buns horizontally with blades that maintain a consistent hinge or full separation depending on format. Slice depth is controlled because it affects later toasting behavior and bun strength during assembly. Sesame seeding, if used, is applied either before baking for adhesion or after with an adhesive wash, depending on equipment design. For high volume distribution, buns are often frozen. Freezing protects softness and allows stable inventory. Buns enter a freezing tunnel where surface is frozen quickly to maintain shape. Packaging then seals buns in bags with barrier properties that limit dehydration. Bag seals must be strong because freezer burn dries bun surfaces and changes toasting behavior. Cheese slices, pickles, onions, and sauces are produced as separate streams with their own controls. But in the context of assembly readiness, the main requirement is portion uniformity and stable handling. Cheese is portioned into slices with tight thickness. Pickles are cut to consistent thickness, so acidity and crunch are predictable per unit. Dehydrated onions are produced by slicing onions and drying them to a low moisture level, then sizing flakes, so rehydration in the final product is consistent. Sauces are mixed as emulsions with defined viscosity, so dispensing systems deliver repeatable weights. Packaging and logistics are treated as part of the production system because the end product depends on thaw and cook behavior. Frozen patties are boxed in counts that match downstream loading systems. Boxes are designed to stack without crushing product. Buns are packaged to reduce moisture loss and protect shape. Temperature stability through storage is critical because freeze-thaw cycles create ice crystals that damage texture and cause condensation inside packs. The final operational transformation happens at the cooking line, where frozen patties are separated and cooked on a clamshell grill. The clamshell grill is engineered for repeatability. Patties are loaded onto a lower hot platen, and then a top platen closes to contact both sides. Contact cooking on both sides reduces cook time and ensures uniform heat penetration. Time and platen temperature are fixed, which is why patty thickness and mass upstream must be consistent. The surface imprint on the patty increases contact and helps fat render evenly. Watermelon slice candies are made by building a flavored sugar gel, shaping it into thick sheets or wedge forms, drying it to a defined chew, then finishing it with a sugar coat that gives the familiar grainy surface and prevents sticking. Production starts with the base syrup because every later step depends on solids level and water activity. Granulated sugar is screened to remove clumps and to keep crystal size consistent. Glucose syrup is stored in jacketed tanks so it can be pumped at a steady viscosity. Water is filtered and tempered because temperature affects how fast sugar dissolves and how stable the cook is. Acid powders and salt are staged in microfeeders because small shifts change sour balance and also change gel strength. Colors and flavors are staged as concentrates, so dosing stays precise when the line runs at high speed. A clear sugar solution is prepared first. Sugar and water enter a dissolver with strong agitation so crystals hydrate without settling. The dissolver runs until the solution is fully clear because undissolved grains can seed crystal growth later. Strainers remove any stray solids that could trigger graining or clog injectors. The clear solution then feeds a cooker, where heat drives off water and raises solids to a target level. Cooking is controlled by temperature and residence time, rather than by appearance. The goal is a repeatable solids concentration that will gel cleanly and dry predictably. If solids are too low, the candy dries slowly and stays sticky. If solids are too high, the gel sets too firm and can crack when cut. Glucose syrup is metered into the cook as a crystallization control tool. It reduces unwanted graining and keeps the final texture smooth rather than sandy. Once the syrup reaches target concentration, it is cooled to a blending temperature. Cooling is staged through heat exchangers so the syrup remains fluid but no longer threatens sensitive ingredients. acid is usually not added at peak heat because low pH at high temperature accelerates inversion and can change chew. Instead, acid is added after cooling as a solution for rapid dispersion. pH is checked because it influences flavor brightness and also affects how some gel systems are set. The gel system is prepared in parallel because it needs hydration time. Many watermelon slice candies use gelatin as the primary gelling agent, sometimes supported by starch or other hydrocolloids. Gelatin is bloomed in cold water, so granules swell evenly. It is then warmed gently until it becomes a clear solution. If starch is used, it is hydrated as a slurry and then cooked to develop viscosity. If other hydrocolloids are used, they are dispersed under high shear to prevent fisheyes and clumps. The cooled syrup and the gel stream meet in an inline mixer. The mixing goal is uniformity without air entrainment. Air bubbles create weak zones and cause cloudy spots in a translucent candy. Static mixers are often used because they create strong folding without whipping. The blended mass becomes a hot, viscous liquid that will set into an elastic gel as it cools. Flavor and color are added late. Watermelon flavor is usually a blend of volatile components that can be stripped by heat, so it is injected after the syrup has been cooled into the safe range. Oil-based flavor components are emulsified or carried so they disperse evenly. Color is added as 2 or 3 separate streams because the finished candy needs distinct layers. A typical slice has green at the rind, white as a thin buffer, and red or pink as the main body. Black or dark inclusions can be added to simulate seeds, but many styles keep a clean surface and rely on printing or speckling in the red layer. To create the layered look, the line either runs sequential casting into one mold or runs separate sheets that are laminated. In sequential casting, the green layer is deposited first into a flat tray or onto a belt. That layer is allowed to partially set so it can support the next deposit without mixing. A thin white layer is deposited next and partially set again. The red layer is deposited last and forms the bulk thickness. Timing is critical because if the first layer is too liquid, the colors bleed. If it is too firm, the layers do not bond and can delaminate later. In lamination-based production, each color is cast as its own thin sheet and cooled to a gel stage. The sheets are then brought together in a laminator that presses them into a single composite slab. Pressing must be firm enough to eliminate air at the interfaces. It must not be so firm that it squeezes layers unevenly. Lamination gives strong layer definition and allows each layer to be tuned for thickness more easily. Once the slab is formed, it is set and pre-dried. Setting brings the gel network to strength so it can be handled. Pre-drying begins moisture reduction so the slab can be cut cleanly later. In starch-molded systems, the candy sets in cavities formed in starch. But watermelon slices are often made as slabs because wedges cut more efficiently from a sheet. Slab setting is done in controlled air rooms where temperature and humidity are managed to avoid sweating. Drying is the step that creates the final chew. Fresh gel has more water than the finished candy. Drying moves the candy into a narrow moisture window where it is elastic and bite resistant without being sticky. Airflow removes moisture from the surface, and then moisture diffuses outward from the interior. Drying must be slow enough to avoid case hardening. Case hardening creates a tough skin and a soft core. The line uses staged humidity and temperature so the surface does not seal too early. As the slab dries, it becomes firmer and more cut stable. At this stage, seed effects can be introduced if the product uses them. Seeds can be small, dark sugar bits that are added during the red deposit. They can also be printed later, but printing is less common on sugar-sanded gummies because the surface is rough. When seed bits are used, they must be dry and stable, so they do not bleed color into the gel. After drying, the slab moves to cutting. Cutting begins with edge trimming because slab edges often have thickness variation from casting. Trims are collected for controlled rework depending on the recipe and moisture state. The slab then passes through a strip cutter that makes long bands at the width of a slice. A second cutter stamps or slices wedges from the bands. Wedge geometry is defined by the cutter profile and by the band width. Cutter speed is synchronized to belt motion, so piece weight stays consistent. Cut quality depends on slab temperature. If the slab is too warm, it smears and sticks to blades. If too cold, it can crack at the layer interfaces. Many lines use chilled, but not cold cutting conditions to get clean edges without fracture. Blade coatings and blade wiping systems reduce buildup. Some plants use ultrasonic blades because vibration reduces sticking on gummy textures and produces smoother cuts. Once wedges are cut, they often undergo a short conditioning stage. This allows cut faces to dry slightly so the pieces do not stick together. Conditioning also equalizes moisture after cutting because freshly exposed interiors release water more quickly. Controlled air prevents surface tack that would ruin the later sugar sanding. Sour balance is built in two places. Some of it is inside the gel through acid dosing. The sharp initial sour that many watermelon slices deliver often comes from the surface. Surface sour is applied by a sanding mix that combines fine sugar with acids, like citric and malic. The blend particle size is controlled so it clings evenly and dissolves at the intended speed. If particles are too fine, they cake. If too coarse, they fall off during conveying. To make sanding adhere, the candy surface needs controlled tack. The surface cannot be wet because the sugar will dissolve and form patches. It cannot be too dry because the sugar will not bond. Many lines use a very light mist of water or syrup to create temporary tack. The mist is extremely fine, so it wets only the outermost surface. Immediately after misting, the wedges enter a sanding drum, where the sugar acid blend is dosed and distributed by tumbling. Tumbling intensity is tuned to protect edges. Wedges have pointed tips and thin green rims that can chip. Drum speed and fill level are chosen to encourage rolling rather than sliding. Rolling spreads, sanding evenly across the faces and edges. After sanding, excess sugar is screened off and collected. A short drying tunnel follows. So, the tack layer sets and the sugar crystals lock onto the surface. Apples become a uniform retail product inside a packing facility by being stabilized, cleaned, sorted, graded, waxed, and packed under tight control of temperature, moisture, and impact. The process starts when bulk field bins of apples enter a receiving line that is designed to keep bruising low. The bins are tipped by a hydraulic dumper into a water flume or a dry cushion infeed. A flume is often used because water supports the fruit and reduces drop impact. Flow rate is set so apples separate and do not pile up. If a dry infeed is used, soft belts and low drop chutes spread the fruit into a single moving layer. From the infeed, the apples pass through a pre-rinse stage that removes loose dust and leaf fragments. Spray bars deliver water at controlled pressure, so surface debris lifts without forcing water into the stem cavity. The rinse water is filtered continuously because suspended grit can scratch skins. The fruit then moves into a washer where rotating brushes scrub the surface. Brush stiffness is chosen by variety because thin-skinned apples mark more easily. Brush speed is tuned so the fruit rotates and contacts brushes evenly instead of sliding. After brushing, the apples pass under high-volume rinses that flush away loosened residues. Drain belts and air knives remove excess surface water. Drying matters because downstream optical cameras need a stable surface reflectance. Drying also matters because wax application behaves differently on wet skins. The line often uses warm air tunnels to bring the surface to a consistent dryness without heating the fruit core. Before deep sorting, the line removes obvious non-conforming fruit mechanically. A sizing roll section can separate very small fruit that will be routed to other packs. A singulation belt then spreads apples into a consistent spacing. Singulation is one of the most important steps because all later measurement systems assume each apple is isolated. Belt speeds and lane dividers maintain spacing as fruit enters the inspection zone. Optical inspection is the central grading step. Multi-angle cameras capture images of each apple as it rotates on rollers. Lighting is controlled to reveal color, gloss, and surface defects. Algorithms measure diameter, shape, blush coverage, and background color. They also detect bruises, punctures, russeting, scab, hail marks, and stem cavity damage. Some lines add near-infrared sensing to estimate internal defects or maturity indicators. The result is a decision for every apple that determines its pack grade and its destination lane. At the same time that cameras inspect surface quality, the system measures size and weight. Size is derived from image geometry and from mechanical calipers in some designs. Weight is measured by in-motion scales that momentarily support the apple and record load. Size and weight are combined because many pack specs are defined as count per carton. Count targets require tight weight distribution, so the packed box stays within tolerance while keeping visual uniformity. Once each apple has a grade and size assignment, the line uses diverters to route it to the correct channel. Diverters can be air jets or flap gates or servo paddles. Timing accuracy is critical because fruit is moving continuously. Each apple's position is tracked from the cameras to the diverter, so the correct gate fires at the correct moment. Mistiming causes cross-grade contamination and forces rework. Many packing lines apply wax after washing and before final packing. Wax is not just cosmetic. It reduces moisture loss and stabilizes gloss. Wax is applied as a fine mist or a roll coat while apples rotate. The wax formula is chosen to form a thin continuous film without streaking. Application rate is controlled because heavy wax can look cloudy and can trap dust. After wax application, the fruit passes through a drying tunnel. Warm airflow sets the film and fixes shine. If stickers are applied, they are placed after waxing and after the surface is dry. A label head peels the sticker and presses it onto the fruit with controlled force. Placement is consistent, so labels do not wrinkle over lenticels or curve edges. The label system is synchronized to fruit spacing, so every selected apple receives one label and the label stays aligned. At this point, the line can split into two main product routes. One route is whole fruit packing. The other route is further processing into fresh cut slices or value packs. For whole fruit packing, the apples enter a packing accumulator that buffers flow. From there, they feed into either tray packing or loose fill systems. Tray packing uses molded fiber or plastic trays that hold each apple in a pocket. Tray selection is based on size count. A tray denester places an empty tray on a conveyor. Apples are then placed into pockets by synchronized drop lanes or robotic pick heads. Pocket depth and spacing reduce movement in the carton and protect skins from rubbing. Loose fill packing is used for bags or bulk cartons. In this route, apples drop into a bag former or into a carton with controlled drop height. Chutes are lined and curved to minimize impact. For bagging, a weighing system portions a target mass. Apples are released into a plastic bag and the bag is sealed. Bag seal timing is coordinated with the drop, so no fruit is caught in the seal. For bulk cartons, the system fills in layers to avoid tall drops. A leveling gate can settle apples into a stable arrangement. Carton formation is integrated into the packing line. Flat blanks are erected into cartons by a case erector. Trays or loose apples are loaded into the carton. A top pad can be placed to reduce scuffing. The carton is then closed and taped or glued. Coding prints a lot identifier and pack information. Check weighers can verify carton weight against expected range. Vision checks can confirm proper closure. A critical part of apple production is storage management inside controlled conditions. Many apples are held in cold storage before packing. Cold storage slows respiration and maintains firmness. Temperature is held near a set point and humidity is controlled to limit dehydration. Many systems use controlled atmosphere storage where oxygen is reduced and carbon dioxide is managed. This slows metabolic activity and preserves texture. Before packing, fruit is often tempered to a target temperature, so condensation does not form on skins when the fruit hits warmer air. Tempering also stabilizes wax behavior and camera performance. When the product route is fresh cut apples, the process changes after washing and sorting. Only fruit that meets internal quality targets is selected because cutting amplifies defects. Selected apples enter a coring and slicing system. The apple is centered by a cup and then pushed onto a corer. The corer removes the core and seeds in one stroke. Slicing blades then cut the apple into wedges or rings. Blade sharpness is tightly maintained because dull blades crush tissue and accelerate browning. The slicing system is designed to keep cut surfaces clean and consistent thickness. Fresh cut apples require anti-browning control. Immediately after slicing the pieces, enter a dip or spray treatment that slows enzymatic browning. The treatment is metered and contact time is controlled. Excess solution is removed by drainage and gentle air. The slices are then portioned into packs. Portioning can be done by weight or by piece count. Packs are sealed with films that control moisture and gas exchange. Some packs use modified atmosphere to slow oxidation. Sealed packs are chilled quickly to stabilize texture. Whether whole or sliced, the final steps focus on protecting quality through handling. Conveyors are designed with soft transfers. Drop heights are minimized. Accumulation tables prevent jams that would compress fruit. Packaging materials are chosen to resist moisture transfer and to maintain structure in cold environments. Cases are palletized in stable patterns that allow airflow during cold chain storage. Mangoes become a consistent retail product inside a packing facility by being stabilized, cleaned, heat treated when required, graded by size and maturity, cooled, waxed, and packed under tight control of temperature and impact. The process begins with bulk field bins or crates entering a receiving line designed to limit bruising. Mangoes are tipped by a hydraulic dumper into a water flume or onto cushioned belts. A flume supports the fruit and reduces drop energy. Water flow is adjusted so mangoes separate and do not stack. If a dry dump is used, the system relies on soft curtains and stepped chutes to spread fruit into a single moving layer. From in feed, the fruit passes through a pre-rinse stage that removes dust and sap residues loosened during harvest and transport. Spray bars deliver water at controlled pressure so the skin is cleaned without forcing water into lenticels. The rinse stream is filtered continuously because grit in recirculated water can scratch skins. Mangoes then enter a washer where rotating brushes scrub the surface. Brush stiffness is selected by variety because skin sensitivity varies. Roller speed is tuned so each fruit rotates and contacts brushes evenly. A key mango-specific step is sap management. Mango latex can mark skins and cause dark streaks. The wash sequence is configured to remove sap films early. Water temperature and contact time are controlled to lift residues without softening the skin. After brushing, high-volume rinses flush away loosened residues. Drain belts and air knives remove surface water, so downstream, sensors see a consistent surface reflectance. Many mango lines include a hot water treatment step when required by export specifications or when a heat treatment is used to stabilize quality. The treatment uses a temperature-controlled water bath with precise residence time. Mangoes enter baskets or carriers that submerge them uniformly. Water temperature is monitored continuously because small deviations change treatment effectiveness and can also stress the fruit. Residence time is controlled by conveyor speed or basket dwell. After treatment, mangoes exit and move immediately to cooling. Cooling is staged to remove heat without creating surface condensation. A first cooling step can use a water rinse at controlled temperature. A second step uses forced air cooling tunnels to bring fruit to a target core temperature. Airflow is designed to reach all sides without creating localized cold spots. Temperature equalization matters because uneven cooling can create localized ripening differences. After washing and any treatment, the fruit enters singulation. Singulation spreads mangoes so each piece can be inspected and measured individually. Lane dividers and timing belts create consistent spacing. Proper spacing is required for accurate imaging and for correct diverter timing. Mangoes then move into an inspection zone where lighting and camera angles are controlled. Optical grading is used to classify mangoes by size, color, shape, and surface defects. Cameras capture multiple views as mangoes roll over rollers. Lighting is configured to reveal bruises, scuffs, sap burn marks, blemishes, and sunspots. Algorithms measure size and estimate volume. Some systems use near-infrared sensing to estimate internal maturity indicators such as dry matter or internal defects. The purpose is to route fruit into ripeness programs and pack grades. Weight grading can be added with in-motion scales. Each mango passes over a support that records weight. Weight data is combined with size data to assign a count class for cartons. Consistent count class is important because cartons are sold by count and expected to look uniform. The system routes mangoes into lanes that correspond to target count and grade. Maturity management is a central control point for mango packing. Mangoes continue ripening after harvest. The facility often receives fruit at different maturity levels. Sorting can separate greener fruit for longer distribution from more colored fruit for near-term delivery. When maturity sensors are used, the system can build lots with consistent dry matter and color stage. This reduces mixed ripeness in a single carton. Once each mango is assigned a destination lane, diverters route the fruit. Diverters can be servo gates or drop belts that release fruit into the correct lane. Timing is precise because mangoes are moving continuously. Impact control at diversion points is critical because mangoes bruise easily. Chutes are lined and curved. Drops are kept low. Accumulators are used to prevent pileups. After grading many lines, apply a wax or coating. The coating reduces moisture loss and improves appearance. Wax is applied as a fine mist while fruit rotates. Application rate is controlled because heavy wax can create streaks and trap dust. After waxing, mangoes pass through drying tunnels where warm air sets the film. Drying air is controlled so it sets wax without warming the fruit excessively. If stickers are required, they are applied after wax and after the surface is dry. A labeling head places a sticker at a consistent position. Placement force is controlled so the sticker adheres without tearing the skin. Label application is synchronized with fruit spacing, so no fruit is missed and no double labels occur. Packing begins with staging fruit into packing buffers. Buffers equalize flow and allow packers to fill cartons at steady speed. Mango packing often uses trays or single-layer cartons to reduce bruising. Tray packing uses molded inserts with pockets. Pocket size is matched to mango size class. Fruit is placed into pockets by synchronized lanes or by pick systems. Pocket orientation is controlled, so stem ends are positioned consistently when required by presentation standards. For loose fill or bulk cartons, The line uses gentle filling chutes. Mangoes are layered rather than dropped in a deep pile. Layering reduces pressure on lower fruit. Pads or liners can be placed between layers. The objective is to prevent pressure points that become bruises. For bag formats, mangoes are weighed into target weights and dropped into bags with controlled drop height. Bags are sealed and then packed into cases. Carton erection and closing are integrated into the line. Flat blanks are erected into cartons by a case erector. Trays or loose fruit are loaded. The carton is closed and taped or glued. Codes are printed to identify lot and pack date. Check weighers confirm cartons are within tolerance. Vision systems can confirm closure integrity. Cold chain control continues after packing. Mangoes are moved into cold rooms set to a target temperature that slows ripening without causing chilling injury. Temperature set points depend on variety and maturity stage. Airflow in. Storage is designed to cool cartons evenly. Humidity is controlled to reduce dehydration while preventing condensation. Carton vents align to allow airflow through the stack. Some supply chains use controlled atmosphere storage or transport. Oxygen and carbon dioxide levels can be adjusted to slow metabolism. Gas control must be stable because excessive carbon dioxide can cause off flavor and internal injury. Even without controlled atmosphere, the core control is maintaining stable temperature through storage and transport. If the facility also produces fresh cut mango, the process branches after grading. Only fruit meeting internal quality targets is selected. Mangoes are peeled using mechanical peelers or knife systems that remove skin with minimal flesh loss. Flesh is sliced from the seed with guided blades. The slices are cut into cubes or strips with calibrated cutters. Cut size is controlled because it affects drainage and pack appearance. Cut pieces are chilled quickly to slow softening. They are portioned into packs by weight and sealed. Packaging films are selected to manage moisture and oxygen exchange.